Observer effect, quantum mechanics. Does reality exist if no one is looking? Imagine you're sitting in a quiet room and everything around you seems still, predictable, and tangible. You believe that objects, whether a book on a table or the moon in the sky, exist independently whether or not you're watching them. But what if I told you that in the realm of quantum mechanics, the very act of observing something changes its behavior? It raises a profound question. Does reality exist if no one is looking? The observer effect emerged from the baffling discoveries of quantum physics in the early 20th century. Classical physics, the domain of Newton and Maxwell, paints a world that's orderly and deterministic. Drop a ball and gravity pulls it to the ground. But quantum mechanics, studying particles like electrons and photons, unveils a strange, probabilistic world where outcomes aren't fixed until we measure them. The roots of this paradox lie in the famous double-slit experiment, first conducted by Thomas Young in the early 1800s. Initially, it demonstrated that light behaves like a wave. But when scientists later applied the experiment to electrons, they noticed something extraordinary. Electrons acted like waves when unobserved, creating an interference pattern on a screen. However, once a measuring device was placed to observe the electrons passing through the slits, the interference pattern disappeared, and the electrons behaved like particles instead. This simple yet puzzling experiment forced scientists to confront an unsettling truth. The mere act of observing particles alters their behavior. What does this mean for the nature of reality? Could observation itself shape the universe? To unravel the observer effect, let's simplify the double-slit experiment with an analogy. Imagine a gardener watching fireflies in a garden. From a distance, the fireflies flit around freely, creating a mesmerizing, unpredictable dance. But when the gardener shines a flashlight to observe them closely, their behavior changes. They become more organized or even scatter. In the quantum world, particles like electrons are the fireflies, and the flashlight is akin to the measurement tool. The heart of this paradox lies in the concept of wave-particle duality. Quantum objects exist as waves of probability, meaning they don't have fixed positions or states until we measure them. Once observed, this wave collapses into a definite state, a particle with a specific position. In other words, observation crystallizes reality from a field of possibilities into a single outcome. But how? One explanation comes from the Copenhagen interpretation, proposed by physicists Niels Bohr and Werner Heisenberg. It suggests that quantum systems don't possess definite properties until measured, and that our observation essentially brings those properties into existence. The observer effect challenges our deepest assumptions about reality. In everyday life, we assume the world exists independently of our perception. But in quantum mechanics, observation plays a fundamental role, blurring the line between the observer and the observed. 1. The role of consciousness. Some scientists and philosophers argue that consciousness itself may influence the outcome of quantum events. This idea suggests a profound link between the mind and the fabric of reality. Does our awareness shape the universe? Could reality be, at least in part, a product of our perception? Such questions evoke parallels with ancient philosophical traditions. In Hinduism and Buddhism, reality is often described as a mental construct shaped by perception. Similarly, George Berkeley, an 18th century philosopher, proposed immaterialism, claiming that objects exist only as ideas in the minds of observers. The observer effect breathes new life into these age-old perspectives, offering scientific grounds to explore the enigmatic relationship between consciousness and existence. 2. Quantum technology and practical applications. Beyond its philosophical intrigue, the observer effect has practical implications. Quantum mechanics underpins revolutionary technologies like quantum computing and quantum cryptography. In quantum computing, for instance, qubits rely on superposition, existing in multiple states simultaneously until measured. Mastering the observer effect is crucial for developing more powerful and reliable quantum systems. Furthermore, quantum cryptography leverages this phenomenon to ensure secure communication. Any attempt to eavesdrop on a quantum encrypted message inevitably alters its state, immediately alerting the intended recipient to the breach. 3. Implications for reality itself. The observer effect also forces us to reconsider the nature of reality. If particles don't have definite states until observed, what does this imply about the universe when no one is watching? Could unobserved phenomena exist in a state of pure potentiality, waiting for consciousness to bring them into being? Some theorists even speculate that the universe might function like a vast quantum computer, processing information through interactions between observers and observed systems. The observer effect leaves us with a profound and unsettling mystery. Is reality dependent on observation, or does it exist independently of our perception? While quantum mechanics has unraveled many of nature's secrets, it has also revealed the limits of our understanding. Perhaps in our quest to comprehend the universe, we're simultaneously shaping it, one observation at a time. As you ponder these questions, imagine the countless unobserved phenomena unfolding across the cosmos. Are they waiting for an observer to give them form? Or do they transcend the need for observation, existing in ways we may never fully grasp? Let the mystery guide your curiosity as the dance between the observer and the observed continues, shaping the very essence of existence. Schrödinger's cat paradox. Can a cat be both alive and dead at the same time? Picture this. A sealed box sits before you, perfectly ordinary on the outside. But inside that box, something extraordinary and deeply unsettling is happening. There's a cat in there, along with a strange mechanism tied to a quantum particle. You're asked a simple question. Is the cat alive or dead? The answer, according to classical logic, should be one or the other. Yet, quantum mechanics tells us something mind-bending. Until you open the box and observe the cat, it is somehow both alive and dead at the same time. This bizarre scenario isn't a twisted science fiction plot, it's a real thought experiment known as Schrödinger's cat, one that has perplexed scientists and philosophers for decades. But how can something exist in two contradictory states at once? Let's explore how this paradox came to be and what it tells us about the strange nature of reality. The Schrödinger's cat paradox was first proposed in 1935 by the Austrian physicist Erwin Schrödinger. By this time, quantum mechanics had already transformed our understanding of the universe at the smallest scales. But it came with a host of strange and unintuitive concepts, chief among them the idea of superposition. Superposition refers to the ability of a quantum system, like an electron or photon, to exist in multiple states at once. For example, a particle could be spinning both clockwise and counterclockwise simultaneously, or it could be in two places at once, until it is measured. Once observed, the particle's state collapses into a single, definite outcome. Schrödinger was deeply troubled by this idea, especially when it came to applying quantum rules to the macroscopic world. To illustrate the apparent absurdity of superposition when scaled up to everyday objects, he devised his now famous thought experiment involving a cat, a box, and a quantum-triggered mechanism. Let's break down Schrödinger's thought experiment in simple terms. Imagine a sealed box containing the following components. 1. A cat. Poor thing, it didn't ask to be part of this bizarre scenario. 2. A radioactive atom that has a 50% chance of decaying within an hour. 3. A Geiger counter that detects radiation from the atom if it decays. 4. A poison vial connected to the Geiger counter, which releases poison and kills the cat if the atom decays. Now here's the twist. After 1 hour, quantum mechanics tells us that the radioactive atom exists in a superposition of decayed and undecayed states. Since the Geiger counter and the poison vial are directly tied to the atom state, they also exist in a superposition, meaning the cat, too, is in a superposition of being both alive and dead. According to quantum theory, it's only when you open the box and observe the cat that the superposition collapses into one definite state, either alive or dead. Until that moment, the cat exists in this strange dual state, embodying a paradox that defies common sense. Schrödinger's cat is more than just a quirky thought experiment. It's a profound metaphor for the peculiar behavior of quantum systems and their interaction with the macroscopic world. Let's explore its implications. 1. The nature of reality. Objective or observer-dependent? At its core, Schrödinger's cat forces us to question whether reality exists independently of observation. In the classical world, we assume that objects have well-defined properties whether or not we're looking at them. A book on a table doesn't vanish into uncertainty when you leave the room. It remains a book. But in the quantum realm, observation plays a crucial role in determining the state of a system. Until observed, particles exist in a probabilistic cloud of possibilities. This raises the unsettling idea that reality itself may be inherently observer-dependent, meaning that what we perceive as real is shaped by our act of observing it. This concept aligns with the Copenhagen interpretation of quantum mechanics, championed by Niels Bohr. According to this view, quantum systems don't have definite properties until measured, and the act of measurement creates reality. Schrödinger's cat exemplifies this interpretation on a macroscopic scale, highlighting how deeply bizarre the quantum world truly is. 2. Many worlds interpretation, a universe of infinite possibilities. While the Copenhagen interpretation suggests that observation collapses the cat's superposition into a single reality, there's another, equally mind-bending explanation: the many worlds interpretation, proposed by Hugh Everett in 1957. According to this theory, when you open the box, the universe splits into two parallel realities. In one, the cat is alive; in the other, it is dead. Both outcomes exist simultaneously, but in separate, non-communicating branches of the universe. This interpretation eliminates the need for collapse and suggests that every possible outcome of a quantum event happens in a vast multiverse of branching realities. If true, it means that countless versions of you exist, each experiencing a slightly different version of reality. While this idea may sound like science fiction, it has serious proponents in the scientific community and offers a way to reconcile quantum mechanics with the deterministic nature of classical physics. 3. Implications for consciousness and free will. The Schrödinger's cat paradox also raises profound questions about the role of consciousness in shaping reality. Does the cat's fate remain undecided until a conscious observer opens the box? If so, does this mean that consciousness has a special role in determining the fabric of the universe? Some interpretations of quantum mechanics, like Wigner's friend thought experiment, suggest that observation, and by extension consciousness, may play a fundamental role in collapsing quantum states. While this idea remains speculative, it has fueled philosophical debates about the nature of consciousness, free will, and the relationship between mind and matter. While Schrödinger's cat may seem like an abstract philosophical exercise, its underlying principles have real-world applications. Quantum superposition is a cornerstone of quantum computing, where qubits can exist in multiple states simultaneously, enabling vastly more powerful computations than classical bits. Additionally, quantum mechanics underpins technologies like MRI machines, semiconductors, and quantum cryptography, all of which rely on the strange behavior of particles at the smallest scales. Without our understanding of quantum superposition, many modern technologies would be impossible. As we close the box on Schrödinger's cat, we're left with more questions than answers. Is reality an objective entity, or is it shaped by our observation? Does the universe branch into countless parallel realities, or does observation collapse possibilities into a single outcome? Perhaps the true lesson of Schrödinger's cat isn't about finding definitive answers, but about embracing the mysteries of existence. Reality, like the cat in the box, may be far more complex and enigmatic than our minds can comprehend. As you ponder these questions, consider the countless unseen events unfolding around you. Are they waiting, like Schrödinger's cat, for someone to observe them and bring them into being? Or do they exist independently beyond the reach of our perception? In the end, Schrödinger's cat invites us to peer into the unknown and wonder what truly lies inside the box of reality. Bootstrap paradox, time travel. What if the origin of an idea doesn't exist? Imagine you find an old, dusty book on advanced mathematics. You study it, master its contents, and grow up to become a brilliant mathematician. One day, you decide to travel back in time, taking that same book with you. Upon arriving in the past, you hand the book to your younger self, ensuring that they too will learn from it and repeat the same journey. But here's the mind-bending twist. Where did the book originally come from? This is the essence of the bootstrap paradox. a paradox of time travel that challenges our understanding of causality, existence, and the very concept of origin. How can something exist without ever being created? Let's dive into the depths of this fascinating paradox and explore what it reveals about time, causality, and reality itself. The term bootstrap paradox takes its name from the phrase, pulling yourself up by your own bootstraps, an impossible task meant to illustrate a self-contained, circular process. In the context of time travel, it describes a situation where an object, piece of information, or even a person is caught in a causality loop with no clear point of origin. The concept first gained popularity in science fiction, with one of the earliest examples appearing in Robert A. Heinlein's 1941 short story By His Bootstraps, which revolves around a protagonist interacting with multiple versions of himself through time loops. Later, movies like Terminator, Predestination, and even Doctor Who episodes featured the paradox, cementing its place in popular culture. But beyond science fiction, the bootstrap paradox raises serious philosophical and scientific questions. If time travel were possible, how could something exist without a cause? Would this violate the principle of causality, the idea that every effect must have a cause? And if so, what does that mean for our understanding of reality? To grasp the bootstrap paradox, we first need to understand causality loops, situations where cause and effect form a closed, circular chain. Unlike our everyday experience of cause leading to effect in a linear sequence, a causality loop means that the cause of an event is also its effect, creating a self-sustaining cycle. Let's break this down with a simple analogy. Imagine a scientist invents a time machine. One day, while working in their lab, they receive a blueprint for that very time machine from a future version of themselves. Following the blueprint, they build the time machine and later travel back in time to hand the blueprint to their younger self. The question is, who originally designed the time machine? The blueprint has no true point of origin. It exists in a causality loop, with its existence sustained by the act of time travel. This creates a paradox because it defies our intuitive understanding of how things should come into being. In our everyday world, everything has an origin, a beginning. But in the bootstrap paradox, objects or information seemingly come from nowhere, existing eternally in a loop without a starting point. The bootstrap paradox opens a Pandora's box of philosophical and scientific questions, challenging long-held notions about reality and causality. Let's explore some of its key implications. 1. Does the bootstrap paradox violate causality? In classical physics, causality is a fundamental principle. Every event has a cause, and that cause precedes the event in time. However, the bootstrap paradox seems to violate this principle by creating a loop where cause and effect are indistinguishable. Some physicists argue that such paradoxes suggest time travel is impossible because they would break the laws of physics as we understand them. Others, however, propose that causality loops could exist without contradiction if time itself is viewed as a closed loop rather than a linear progression. This idea aligns with certain interpretations of general relativity, particularly solutions involving closed time-like curves, paths through space-time that allow an object to return to its own past. While these solutions are mathematically possible, they remain speculative, as we have no empirical evidence of time travel or causality loops in the real world. 2. The ontological paradox: existence without creation. At the heart of the bootstrap paradox lies a deeper puzzle known as the ontological paradox. How can something exist without ever being created? In our earlier example, the book of advanced mathematics has no origin. It exists because it is passed between different points in time, but no one ever wrote it. This paradox challenges our understanding of ontology, the branch of philosophy concerned with the nature of being and existence. It suggests that in a universe where time travel is possible, objects or information could exist in a self-sustaining loop, defying the need for a clear origin. In a sense, the bootstrap paradox implies that the universe could contain islands of existence, objects or ideas that exist without a cause, sustained purely by time loops. This raises profound questions about the nature of reality. Is everything we see and experience the result of a linear chain of cause and effect? Or could some things exist simply because they exist? 3. Implications for free will and determinism. The bootstrap paradox also has significant implications for the age-old debate between free will and determinism. If time travel allows for causality loops, does that mean events are predetermined with no possibility of change? After all, if an event's cause is also its effect, it suggests a closed, deterministic system where everything happens as it must, without any room for free will. However, some interpretations suggest that while causality loops may exist, they don't necessarily negate free will. Instead, they could imply a more complex form of agency, where actions taken in the present influence both the past and future in ways that are difficult to comprehend. 4. Real-world analogies and scientific theories. While time travel remains speculative, certain real-world phenomena bear a resemblance to the bootstrap paradox. For example, in quantum mechanics, particles can influence each other instantaneously across vast distances through a process known as quantum entanglement, seemingly defying classical notions of causality. Moreover, theories about the cyclical nature of time, suggesting that the universe may go through infinite cycles of expansion and contraction, bear similarities to causality loops. If time is indeed cyclical, it could allow for scenarios where events have no clear beginning or end, echoing the logic of the bootstrap paradox. As we close this exploration of the bootstrap paradox, we're left with a haunting question. If something can exist without an origin, what does that mean for the nature of existence itself? Could it be that the universe, like the objects in a causality loop, exists without a clear cause, sustained by time or something beyond our understanding? The bootstrap paradox invites us to rethink our assumptions about time, causality, and the universe. It suggests that reality may be far stranger and more complex than we can comprehend, and that, in the grand tapestry of existence, some threads may have no beginning or end. As you ponder these mysteries, consider this. What if your very existence is part of a loop, an endless cycle with no clear origin stretching across time and space? Perhaps, like the paradox itself, the answers lie not in finding a beginning, but in embracing the infinite possibilities of the unknown. Twin paradox, relativity. Why does time pass differently for twins in space? Imagine this. Two identical twins stand side by side on Earth, looking up at the stars. One twin boards a spaceship, embarks on a journey to a distant star, and returns after what feels like only a few years. Meanwhile, the twin who stayed on Earth has aged decades. The two are no longer the same age, despite being born at the exact same moment. How can time, something we experience as constant and unchanging, behave so strangely? This mind-bending scenario is known as the twin paradox, and it's one of the most fascinating consequences of Einstein's theory of relativity. Let's dive into this paradox, explore its origin, and see how it fundamentally reshapes our understanding of time and space. The twin paradox is rooted in Einstein's theory of relativity, specifically his theories of special relativity, published in 1905, and general relativity, published in 1915. To understand the paradox, we need to grasp a key concept from special relativity: time dilation. 1. The speed of light is constant. One of the central principles of special relativity is that the speed of light in a vacuum is always constant, roughly 300,000 kilometers per second, no matter how fast an observer is moving relative to the light source. This might seem counterintuitive at first because, in our everyday experience, speeds add up. If you're on a moving train and throw a ball forward, its speed is the sum of your speed and the ball's speed. But light doesn't behave this way. It travels at the same speed for all observers regardless of their motion. 2. Time slows down for moving objects. To preserve the constancy of the speed of light, time itself must adjust. In other words, time moves slower for objects traveling close to the speed of light compared to stationary observers. This phenomenon is known as time dilation. The faster an object moves, the more pronounced the time dilation becomes. Einstein's equations show that time dilation isn't just a theoretical curiosity. It's a measurable effect. This forms the basis for the twin paradox. One twin travels at near light speed, experiencing significant time dilation, while the other remains on Earth, Experiencing time at a normal rate. To better understand the twin paradox, let's walk through a thought experiment involving two twins, Alice and Bob. 1. The journey begins. Alice stays on Earth while Bob boards a spaceship capable of traveling at 90% the speed of light. Bob's mission is to travel to a distant star 10 light-years away and then return to Earth. 2. Relativistic time dilation. Because Bob's spaceship is traveling at 90% the speed of light, time for him slows down significantly compared to Alice, who remains on Earth. From Alice's perspective, Bob's journey takes about 22 years, 10 years to reach the star and 10 years to return, with an extra 2 years for acceleration and deceleration. However, due to time dilation, Bob experiences far less time passing on his journey. According to the relativistic time dilation equation, he might only experience around 9 years of travel time in total. 3. The reunion. When Bob returns to Earth, he is only 9 years older, while Alice has aged 22 years. Despite being identical twins, they now find themselves at drastically different ages. This discrepancy in aging is the heart of the twin paradox. At first glance, the twin paradox seems to violate common sense. After all, shouldn't both twins experience time dilation relative to each other? If motion is relative, why does only Bob experience less time passing? The key to resolving this apparent paradox lies in the fact that Bob's journey involves acceleration and deceleration, while Alice remains in an inertial frame of reference, a frame moving at a constant velocity. Special relativity applies only to inertial frames, so while Alice can be considered stationary throughout the entire experiment, Bob cannot. When Bob accelerates to near light speed, decelerates at the distant star, and accelerates again for the return journey, he experiences forces that Alice doesn't. These forces break the symmetry between the twins, making Bob's frame of reference different from Alice's. This asymmetry explains why Bob experiences less time passing than Alice. In more advanced terms, general relativity, which accounts for acceleration and gravity, provides a more complete explanation of the paradox. It shows that the path through space-time taken by Bob is fundamentally different from Alice's, leading to the observed difference in aging. The twin paradox isn't just a fascinating thought experiment. It has real-world implications for our understanding of time, space, and the universe. 1. Time is relative, not absolute. The twin paradox underscores a fundamental truth of relativity. Time is not an absolute universal quantity. Instead, it's relative, depending on the observer's frame of reference. This challenges our intuitive notion of time as something that flows uniformly for everyone, everywhere. In our everyday lives, the effects of relativity are negligible because we move at speeds much slower than light. However, at high velocities, such as those involved in space travel, relativistic effects become significant. 2. Space exploration and the future of humanity. As humanity looks toward the stars, the twin paradox offers a glimpse into the strange realities future space travelers may face. Imagine astronauts embarking on journeys to distant star systems at near-light speeds. Upon returning to Earth, they may find that decades or even centuries have passed, while they have aged only a few years. This has profound implications for long-term space exploration. If we ever develop the technology for near-light speed travel, relativistic time dilation will mean that astronauts can effectively skip forward in time, experiencing the future in ways unimaginable to those who remain on Earth. 3. The search for a universal now. The twin paradox also raises deep philosophical questions about the nature of the present. If time is relative, can there be a universal now that encompasses the entire universe? Einstein himself suggested that the concept of a universal present is an illusion, and that past, present, and future are relative concepts, dependent on the observer's frame of reference. This idea challenges our understanding of existence and reality, suggesting that time may be more fluid and less absolute than we commonly believe. Although we don't yet have spaceships traveling at near light speed, the effects of time dilation have been observed in experiments here on Earth. 1. Atomic clocks. Scientists have placed highly precise atomic clocks on airplanes and flown them around the world. When compared to identical clocks that remained stationary on Earth, The airborne clock showed slightly less time had passed, confirming the predictions of special relativity. 2. Particles in accelerators. Particles accelerated to near light speeds in particle accelerators, such as those at CERN, exhibit time dilation. They decay more slowly than particles at rest, providing further evidence that time slows down at high velocities. As we conclude this exploration of the twin paradox, we're left with a profound realization. Time is not a constant. It's a dynamic, relative quantity shaped by motion and gravity. This challenges our everyday understanding of time as something fixed and universal, opening the door to a deeper, more nuanced view of reality. So, the next time you look up at the stars, consider this. What if future explorers traveling at near light speeds return to find a world that has aged beyond recognition? What would it mean for human relationships, for our sense of history, and for our connection to the universe? Perhaps the twin paradox is a reminder that the universe is far stranger and more wondrous than we can imagine, and that our journey to understand it has only just begun. Fermi paradox: where are the aliens? If the universe is infinite, where is everyone else? Look up at the night sky. The vast expanse of stars stretches endlessly, each star potentially harboring planets, each planet possibly teeming with life. Given the sheer number of stars in the universe, hundreds of billions in our galaxy alone, it seems almost certain that intelligent life must exist somewhere out there. Yet, despite decades of searching, we've heard nothing. No signals, no signs, no visitors. This is the heart of the Fermi paradox. If the universe is so vast and ancient, why haven't we encountered any evidence of extraterrestrial civilizations? Where is everyone else? The Fermi paradox is named after the renowned physicist Enrico Fermi, who famously posed the question during a casual lunchtime conversation in 1950. While discussing the potential for extraterrestrial life, Fermi reportedly asked, "Where is everybody?" His question wasn't rhetorical, it highlighted a profound contradiction: the high probability of alien life existing versus the complete lack of evidence for it. 1. The vastness of the universe. To understand why Fermi's question is so compelling, we need to grasp just how immense the universe is. The Milky Way galaxy, our cosmic home, contains roughly 100 to 400 billion stars, many of which have planetary systems. Beyond our galaxy lie billions of other galaxies, each containing billions of stars. Statistically, it's hard to believe that Earth is the only place where intelligent life has evolved. Even if intelligent life is exceedingly rare, say only 1 in a billion stars hosts a civilization, that would still mean millions of advanced civilizations could exist in our galaxy alone. 2. The Drake equation. In 1961, astronomer Frank Drake formulated an equation to estimate the number of advanced civilizations in our galaxy with which we might be able to communicate. The Drake equation looks like this. Drake's equation isn't meant to give a definitive answer, but rather to frame the problem and highlight the many unknowns. Depending on how you estimate the values, the result can range from millions of civilizations to virtually none. Given the immense number of potentially habitable planets, why haven't we detected any signs of intelligent life? Scientists have proposed several possible explanations for the Fermi paradox, each offering a different perspective on why the universe seems so silent. 1. We're alone. The rare Earth hypothesis. One explanation is that Earth is extraordinarily rare and life as we know it is incredibly unlikely to occur elsewhere. According to the rare Earth hypothesis, a series of highly improbable events led to the emergence of complex, intelligent life on our planet, including the presence of a large, stabilizing moon, a magnetic field that protects Earth from harmful radiation, the right combination of chemical elements for life, billions of years of relatively stable climate. If these conditions are exceptionally rare, it's possible that intelligent life exists only on Earth, making us a cosmic anomaly. 2. Civilizations are too distant in space and time. Another possibility is that intelligent civilizations do exist, but they are so far away that communication or travel between them is effectively impossible. Even if there are millions of advanced civilizations in the galaxy, they might be separated by thousands or millions of light years. Given the limitations of physics, specifically the speed of light, it could take millions of years for a signal to travel from one civilization to another. Additionally, civilizations may only last for a relatively short period before collapsing or evolving beyond the need for communication. If advanced civilizations arise and fall in different eras, they may never overlap in time, making contact unlikely. 3. The Great Filter Hypothesis. The Great Filter hypothesis suggests that there is some extremely difficult barrier that prevents life from evolving to the point of interstellar communication. This barrier could occur at any stage in the development of life, such as the origin of life itself, abiogenesis, the emergence of complex multicellular life, the evolution of intelligent beings, the ability to develop advanced technology without self-destruction. If the Great Filter lies ahead of us, meaning that most civilizations self-destruct before reaching interstellar capability, it would explain why we haven't detected any signs of alien life. This idea raises existential questions about the future of humanity. Are we doomed to face the same fate as countless other civilizations before us? 4. They're hiding. The zoo hypothesis. According to the zoo hypothesis, advanced civilizations may be aware of our existence, but have chosen not to contact us. Much like humans observing animals in a zoo, they may prefer to watch us from a distance without interfering in our development. This idea assumes that highly advanced beings would have ethical or philosophical reasons for avoiding contact with less advanced civilizations. Alternatively, they may be waiting for us to reach a certain level of technological or social maturity before revealing themselves. 5. We haven't looked hard enough. It's also possible that intelligent life exists, but we simply haven't looked in the right places or used the right methods to detect it. Our current efforts, such as the Search for Extraterrestrial Intelligence, SETI, rely on detecting radio signals or other forms of electromagnetic communication. However, advanced civilizations might use technologies beyond our understanding, such as quantum communication or something entirely unknown. Furthermore, given the vastness of space, we've only examined a tiny fraction of our galaxy. It's possible that evidence of extraterrestrial life exists, but we haven't found it yet because our search has been too limited. The Fermi paradox isn't just a scientific puzzle. It also has profound implications for humanity's place in the universe and our understanding of existence. 1. Are we special? If we are truly alone in the universe, it would suggest that humanity holds a unique and perhaps even privileged position in the cosmos. This realization could inspire a greater sense of responsibility to protect our planet and ensure the survival of our species, knowing that we might be the only intelligent beings capable of contemplating the universe. 2. Are we doomed? On the other hand, if the Great Filter lies ahead of us, it raises troubling questions about humanity's future. Will we be able to overcome the challenges of technological advancement, environmental destruction, and potential self-destruction? Or are we destined to follow the same path as countless other civilizations that failed to reach the stars? 3. What if they're out there? If intelligent life does exist elsewhere, discovering it would be one of the most transformative events in human history. It would force us to confront new ethical, philosophical, and practical questions about how to interact with other civilizations. Would we be able to communicate? Would they be friendly or hostile? How would such a discovery reshape our understanding of ourselves and our place in the universe? As we gaze at the stars and ponder the Fermi paradox, we're left with a profound sense of mystery. Are we truly alone? Or is the universe teeming with life, waiting to be discovered? Perhaps the silence of the cosmos is a challenge, an invitation to explore, to learn, and to push the boundaries of human knowledge. One day we may find the answer. Until then, the question, where is everyone, will continue to inspire curiosity, wonder, and the relentless pursuit of the unknown. After all, in a universe so vast, the possibilities are as infinite as the stars themselves. Grandfather paradox, time travel. What happens if you go back in time and change your past? Imagine you invent a time machine and decide to embark on a daring journey to the past. You arrive in a small town decades before you were born and Out of curiosity or impulse, you do something unthinkable. You prevent your grandfather from ever meeting your grandmother. Without this meeting, your parent would never have been born, and consequently, you would never have existed. But if you were never born, how could you have traveled back in time in the first place? This mind-bending scenario is known as the grandfather paradox, one of the most famous and perplexing paradoxes in time travel. It raises a profound question. Can you change the past, or is it forever fixed? The grandfather paradox has its roots in the early 20th century when time travel became a popular theme in science fiction. Although the idea of traveling through time dates back to ancient myths and legends, it was H.G. Wells's 1895 novel, The Time Machine, that popularized the concept of time travel in the modern imagination. As scientists and philosophers began to seriously consider the possibility of time travel, they encountered a troubling logical contradiction. If time travel allows someone to alter the past, it could lead to paradoxical situations where the very act of time travel negates the traveler's ability to have existed in the first place. The term grandfather paradox specifically refers to the classic scenario in which a time traveler goes back in time and prevents their own grandfather from having children. Without their grandfather, the traveler would never have been born, creating a logical contradiction. But the paradox isn't limited to family relations. It represents a broader problem with the idea of altering history. To understand the grandfather paradox, let's break it down with a simple analogy. 1. The setup. Imagine a person named Alex invents a time machine in the year 2010. Alex decides to travel back to the year 1950, where his grandfather George is a young man. Out of curiosity, or perhaps due to an unfortunate accident, Alex does something that prevents George from meeting Alex's grandmother. 2. The contradiction. If George never meets Alex's grandmother, Alex's parent will never be born, meaning Alex himself will never be born. But if Alex was never born, how could he have traveled back in time to prevent George from meeting his grandmother? This creates a self-contradictory loop where Alex's very existence is dependent on events that he has now changed. The core problem. The grandfather paradox illustrates a fundamental problem with the concept of time travel. If the past can be changed, it can create situations where the cause and effect relationship breaks down. In this case, the cause, Alex's time travel, negates the effect, Alex's birth, which in turn negates the cause itself, creating an endless loop of logical inconsistency. The grandfather paradox opens up deep philosophical and scientific questions about time, causality, free will, and the nature of reality. Let's explore some of the key implications. 1. Can you change the past? At the heart of the grandfather paradox is the question of whether the past can be changed. In our everyday experience, time flows in one direction, from the past to the present to the future. Cause always precedes effect, and once something has happened, it cannot be undone. However, if time travel were possible, it would challenge this linear view of time. Could a time traveler alter past events, or is the past fixed and unchangeable? Different theories of time travel offer different answers. Fixed timeline theory. According to this theory, the past, present, and future are fixed and unchangeable. Even if time travel is possible, any actions taken by the traveler were always part of history. In other words, you can't change the past because your actions in the past have already happened. This idea is often referred to as Novikov's self-consistency principle, proposed by Russian physicist Igor Novikov. It suggests that time travel might be possible, but paradoxes cannot occur because the universe prevents any actions that would create a contradiction. Dynamic timeline theory. This theory allows for the possibility of changing the past. If a time traveler alters a past event, it would create a new timeline or alternate reality. However, this raises new questions. Would the traveler remain in the altered timeline, or would they return to their original timeline? And if multiple timelines exist, how do they interact? 2. The multiverse theory. Avoiding paradoxes through alternate realities. One way to resolve the grandfather paradox is through the multiverse theory. According to this idea, every time a time traveler changes the past, they create a new parallel universe. In this new universe, events unfold differently, but the original timeline remains unaffected. In the context of our earlier example, when Alex prevents George from meeting his grandmother, he doesn't erase himself from existence. Instead, he creates a new universe where he was never born. Meanwhile, in the original timeline, Alex's birth and time travel still occurred. The multiverse theory avoids logical contradictions by suggesting that time travel doesn't alter a single, fixed timeline, but rather creates branching timelines, each with its own unique history. While this idea is popular in science fiction, it also has some basis in scientific theories, such as quantum mechanics and the concept of parallel worlds. 3. Determinism versus free will. The grandfather paradox also raises important questions about free will and determinism. If time travel is possible but the past cannot be changed, as suggested by the fixed timeline theory, it implies a deterministic universe where all events are predetermined and inevitable. In such a universe, even a time traveler's actions are predestined. They were always part of history and cannot alter its course. On the other hand, if time travel allows for changes to the past, it suggests that free will exists and that individuals can influence the course of events. However, this view leads to paradoxes and logical contradictions, such as the grandfather paradox. The tension between determinism and free will has long been a subject of philosophical debate, and time travel adds a new layer of complexity to this discussion. 4. Real-world time travel. Is it possible? While the grandfather paradox is largely a thought experiment, it's worth considering whether time travel is physically possible. According to Einstein's theory of general relativity, time travel to the future is theoretically possible through time dilation. If an object moves at close to the speed of light or experiences intense gravitational fields, time for that object slows down relative to an outside observer. This has been experimentally confirmed using highly precise atomic clocks on fast-moving airplanes. However, traveling to the past is much more problematic. Solutions to Einstein's equations, such as closed time-like curves, paths through space-time that loop back on themselves, suggest that backward time travel might be possible under certain extreme conditions, such as near a rotating black hole. But even if such solutions are theoretically valid, we have no experimental evidence or practical means of achieving backward time travel. The grandfather paradox forces us to confront some of the deepest mysteries about time, causality, and the nature of reality. Is time an unchangeable sequence of events, or is it a fluid, malleable dimension? If time travel were possible, would we be able to rewrite history, or would we be bound by the self-consistency of a deterministic universe? Perhaps the true lesson of the grandfather paradox is that our understanding of time is still incomplete. As we explore the possibilities of time travel, both in science and in imagination, we may one day find answers to these profound questions. Until then, the paradox remains a fascinating puzzle, inviting us to ponder the nature of existence and the limits of what is possible. So, the next time you wonder what it would be like to travel back in time, ask yourself, if you could change the past, would you? And if you did, who would you become? Perhaps the greatest paradox of all is not whether we can change history, but whether we can ever truly escape the present moment. Arrow of time. Why does time only move forward? Imagine a glass falling off a table, shattering into countless pieces. You can easily picture this happening in real life. But what if you watched a video of the shattered pieces reassembling themselves into a perfect glass and leaping back onto the table? It would seem impossible, unnatural, almost absurd. Yet, if we only consider the basic laws of physics, both scenarios should be equally possible. So why then do we only ever experience time moving in one direction, forward? Why does the past feel fixed, while the future feels uncertain? This mystery is encapsulated in the concept of the arrow of time, a paradox that arises when we realize that the fundamental laws of physics don't distinguish between past and future, but our experience of time does. Let's explore how this paradox emerged and what it reveals about the nature of time, entropy, and the universe itself. To understand the arrow of time paradox, we need to delve into the concept of entropy and the second law of thermodynamics. These ideas form the foundation for understanding why time seems to flow in a particular direction. 1. What is entropy? Entropy is a measure of disorder or randomness in a system. In simple terms, it describes the number of ways a system can be arranged. The more disordered a system is, the higher its entropy. For example, a neatly stacked pile of books has low entropy because it has a very specific and ordered arrangement. In contrast, if you knock over the pile and the books scatter randomly across the floor, the system has many more possible configurations, resulting in higher entropy. The second law of thermodynamics. The second law of thermodynamics states that in a closed system, entropy always increases over time. This means that systems naturally evolve from states of low entropy, order, to states of high entropy, disorder. Importantly, this law introduces a preferred direction of time, forward. Once a pile of books is knocked over, it's highly unlikely that they will spontaneously restack themselves. Once a glass shatters, it won't reassemble on its own. Unlike other physical laws, which are time-symmetric, they work the same whether time moves forward or backward, the second law introduces an asymmetry, a clear distinction between past and future. This asymmetry is what gives rise to the arrow of time. At first glance, the paradox of the arrow of time may not seem obvious. After all, we experience time as moving forward, so isn't that just the way things are? But the puzzling part is that most fundamental laws of physics, such as Newton's laws of motion, Maxwell's equations for electromagnetism, and even Einstein's theory of relativity, are time reversible. This means they don't inherently distinguish between past and future. If you filmed a ball rolling across a floor and then played the video backward, the motion would still obey the laws of physics. So why then do we perceive time as having a forward flow? The answer lies in entropy and the second law of thermodynamics. Entropy as the driver of time's arrow. Consider the universe as a whole. In its early state, shortly after the Big Bang, the universe was in an extremely low entropy, highly ordered condition, a dense, hot, uniform plasma. Over billions of years, the universe has expanded and evolved into a much higher entropy state, with stars, galaxies, and vast amounts of empty space. This increase in entropy gives rise to the perception of time moving forward. Let's return to the example of the shattered glass. The reason we don't see glasses spontaneously reassembling is that such an event would involve a decrease in entropy, which contradicts the second law. The forward flow of time that we experience is simply the direction in which entropy increases. The arrow of time paradox raises profound questions about the nature of time, the universe, and even human existence. Let's explore some of the key implications. 1. Time and human perception. One of the most intriguing aspects of the arrow of time is how it shapes our perception of reality. We experience time as a linear progression from past to future. The past feels fixed and immutable, while the future feels open and full of possibilities. This perception is closely tied to the increase of entropy. For example, we remember events that have already happened, low entropy past, but cannot foresee events that have yet to occur, high entropy future. This asymmetry in memory and prediction is a direct consequence of the second law of thermodynamics. But what if we lived in a universe where entropy decreased instead of increased? Would we experience time flowing backward? This thought experiment challenges our intuitive understanding of time and suggests that our perception of time's arrow may be a product of the physical laws governing our universe. 2. The ultimate fate of the universe. The arrow of time also has profound implications for the future of the universe. According to current cosmological models, the universe will continue expanding, and entropy will keep increasing until it reaches a state of maximum entropy, a state known as heat death. In this state, all energy will be evenly distributed, and no useful work can be done. Stars will burn out, black holes will evaporate, and the universe will become a cold, dark, and lifeless place. This bleak vision of the future raises philosophical questions about the meaning and purpose of life in a universe governed by entropy. If time is an arrow pointing toward inevitable decay, does anything we do ultimately matter? 3. Can the arrow of time be reversed? While the second law of thermodynamics seems to forbid the reversal of time's arrow, Some theoretical physicists have explored scenarios in which time might flow backward. One such idea involves cyclical universes, models in which the universe undergoes endless cycles of expansion and contraction. In these models, time's arrow might reverse during the contraction phase, leading to a universe where entropy decreases. Another speculative idea involves quantum mechanics. In certain interpretations of quantum theory, such as the many worlds interpretation, time doesn't have a single, fixed direction. Instead, all possible timelines exist simultaneously, and what we perceive as the forward flow of time is merely one path through a vast multiverse of possibilities. While these ideas remain speculative, they highlight the fact that our understanding of time is far from complete. The arrow of time paradox invites us to ponder one of the deepest mysteries of existence. Why does time move forward, and what does that mean for us in the universe? While entropy and the second law of thermodynamics provide a compelling explanation for the direction of time, they also raise profound questions about the nature of reality, the ultimate fate of the cosmos, and our place within it. As you reflect on the flow of time, consider this. Is the forward march of time an unchangeable law of the universe? Or could it be an illusion shaped by our limited perspective? Perhaps one day, as our understanding of physics deepens, we'll uncover new truths about time and discover that the arrow we follow is just one of many possible paths through an infinite, ever-evolving cosmos. Until then, the paradox of the arrow of time will continue to inspire wonder, curiosity, and a deeper appreciation for the fleeting, precious moments of existence. Infinite Hotel Paradox, Hilbert's Hotel. Can an infinite hotel ever be full? Imagine you arrive at a hotel late at night. This isn't just any hotel, it's the infinite hotel, with an endless number of rooms, each neatly numbered from 1 to infinity. You're told by the receptionist that every single room is occupied, yet somehow they still manage to find space for you. How is this possible? And if an infinite number of new guests were to arrive, could they all be accommodated too? This strange scenario is known as the Infinite Hotel Paradox, a thought experiment devised by the mathematician David Hilbert. It's a fascinating paradox that forces us to confront the bizarre and counterintuitive nature of infinity. Let's explore how this paradox works, what it reveals about infinity, and its implications for mathematics, logic, and even the cosmos. The Infinite Hotel Paradox was introduced by David Hilbert, a German mathematician, in the early 20th century. Hilbert was one of the most influential mathematicians of his time, known for his work in mathematical logic, geometry, and the foundations of mathematics. Hilbert's Hotel is a thought experiment designed to illustrate the strange properties of infinite sets, collections of objects that, unlike finite sets, don't follow the intuitive rules of arithmetic and counting. While we're used to thinking of hotels as having a finite number of rooms, Hilbert imagined a hotel with countably infinite rooms, meaning there's no upper limit to how many rooms exist. The paradox arises when we try to apply our everyday logic about finite numbers to this infinite system, leading to counterintuitive and paradoxical results. Let's break down the Infinite Hotel Paradox step by step, using a few different scenarios to illustrate its peculiar nature. Scenario 1. A new guest arrives. Suppose the Infinite Hotel is fully occupied, meaning that every room is taken. Now a new guest arrives. In a finite hotel, this would be a problem, as there would be no available rooms. However, in the Infinite Hotel, the receptionist has a clever solution. 1. The receptionist asks each guest to move from room N to room N plus 1. 2. This simple shift frees up room 1 for the new guest, while every other guest still has a room. Despite being fully occupied, the hotel accommodates the new guest by rearranging the occupants. This demonstrates one of the key properties of infinity. You can add to an infinite set without increasing its size in any meaningful way. Scenario 2. An infinite number of new guests arrive. Now, let's make things even stranger. Suppose an infinite number of new guests arrive at the Infinite Hotel. Once again, the receptionist finds a way to accommodate them. 1. The receptionist asks each current guest in room N to move to room 2N, doubling their room number. 2. This rearrangement leaves all the odd-numbered rooms, 1, 3, 5, 7, etc., vacant. 3. The new guests are assigned to these odd-numbered rooms, ensuring that everyone, both old and new guests, has a room. Once again, the infinite hotel, despite being full, manages to accommodate an infinite number of new guests by leveraging the peculiar properties of infinity. Scenario 3. An infinite number of buses with infinite passengers arrive. To push the paradox even further, imagine that an infinite number of buses, each carrying an infinite number of passengers, arrives at the hotel. How can the infinite hotel possibly accommodate this overwhelming influx of guests? The receptionist uses an even more elaborate strategy. 1. First, each current guest in room N moves to room 2 to the power of N, raising 2 to the power of their room number. 2. Next, the passengers on bus 1 are assigned to rooms numbered 3 to the power of M, where M is their seat number on the bus. 3. The passengers on bus 2 are assigned to rooms numbered 5 to the power of M, and so on, using prime numbers to create unique room assignments for each bus and each passenger. Through this ingenious system, the infinite hotel accommodates an infinite number of infinite groups of new guests, demonstrating that infinity, in a mathematical sense, is far more flexible and strange than our everyday intuition suggests. The infinite hotel paradox isn't just a quirky thought experiment. It has profound implications for how we understand infinity, mathematics, and even the universe. 1. The nature of infinity. In everyday life, we deal with finite quantities. Whether we're counting people, objects, or distances, we're always working within limits. Infinity, by contrast, represents something without limits, an unending quantity that defies conventional arithmetic. Hilbert's Hotel illustrates the difference between finite and infinite sets. In a finite set, adding more elements increases the size of the set. But in an infinite set, you can add more elements, even infinitely many, without fundamentally changing its size. This idea is formalized in mathematics through the concept of cardinality, which measures the size of sets. Countably infinite sets, like the rooms in Hilbert's Hotel, have the same cardinality as the set of natural numbers, Nyemathbe, meaning they can be put into one-to-one correspondence with each other. 2. Infinity in cosmology, the infinite hotel paradox, also has intriguing implications for our understanding of the universe. Some cosmological models suggest that the universe may be infinite in extent, with an infinite number of stars, galaxies, and planets. If this is true, Hilbert's Hotel offers a way to think about the strange and counterintuitive properties of an infinite cosmos. Moreover, the paradox raises questions about the nature of time. If time is infinite, does it behave like the rooms in Hilbert's Hotel, where any moment can always be followed by another? Does infinity allow for an endless cycle of creation and destruction, as proposed in some theories of cyclical universes? 3. Paradoxes of infinity and human logic. Hilbert's Hotel highlights the limitations of human intuition when dealing with infinity. Our minds are accustomed to thinking in finite terms, so the idea that a fully occupied hotel can still accommodate infinitely more guests seems paradoxical. This paradox forces us to confront the fact that infinity isn't just a very large number, it's a fundamentally different kind of quantity. Understanding infinity requires us to set aside our everyday logic and embrace a more abstract, mathematical way of thinking. The infinite hotel paradox invites us to ponder the true nature of infinity. If something can be infinitely large, can it ever truly be full? And if the universe itself is infinite, what does that mean for our place within it? Perhaps infinity isn't something we can ever fully grasp, but only something we can explore through thought, imagination, and mathematics. As you reflect on Hilbert's Hotel and the paradoxes of infinity, consider this. Is infinity a concept that exists only in our minds, or is it a fundamental feature of reality? The answer may lie not in finding the limits of what we can know, but in embracing the endless possibilities of what we have yet to discover. Paradox of choice. Why does having too many choices make us less happy? Imagine walking into a grocery store to buy a simple jar of peanut butter. You expect a quick in and out trip, but instead, you're faced with an overwhelming wall of options, creamy, crunchy, organic, sugar-free almond butter, cashew butter, peanut butter infused with chocolate, and dozens more. After spending 20 minutes analyzing labels, you finally make a choice. But as you leave, you feel uneasy? Did I make the right decision? Should I have chosen the organic one instead? Or maybe the one on sale? Ironically, instead of feeling satisfied with your decision, you feel anxious and less happy than if there had been just one or two options. This is the paradox of choice. The idea that while having more options seems like it should make us happier, it often leaves us feeling overwhelmed, dissatisfied, and regretful. Let's explore how this paradox emerged, why too many choices can be paralyzing, and what it means for life in our modern, consumer-driven world. The paradox of choice was popularized by Barry Schwartz, an American psychologist and author, in his 2004 book, The Paradox of Choice: Why More is Less. Schwartz argued that while living in a society that offers an abundance of choices is often seen as a symbol of freedom and self-determination, it can have negative psychological effects, leading to anxiety, regret, and even depression. Schwartz's ideas weren't based solely on theory. They were supported by numerous psychological studies on decision-making and satisfaction. One of the most well-known studies was conducted by psychologists Sheena Iyengar and Mark Lepper in 2000, known as the JAM study. The JAM study. In the study, Iyengar and Lepper set up a tasting booth at a grocery store. In one version, they offered 24 different flavors of jam for customers to try. In another version, they offered only 6 flavors. The results were surprising. While more people stopped at the booth when there were 24 flavors, only 3% of them made a purchase. When only 6 flavors were offered, 30% of people made a purchase, a 10-fold increase in conversion. The study demonstrated that while people are initially attracted to a large number of choices, they're less likely to make a decision or feel satisfied when faced with too many options. This was one of the first empirical demonstrations of the paradox of choice, showing that more options don't necessarily lead to better outcomes. To understand the paradox of choice, we need to break down why having an abundance of options can make decision-making more difficult and less satisfying. Here are some key factors. 1. Decision paralysis. When faced with too many options, people often experience decision paralysis, the inability to make a decision at all. This happens because evaluating a large number of choices requires significant cognitive effort. Our brains can only handle so much information at once, and when overwhelmed, we may choose to avoid making a decision altogether. Analogy. Imagine you're at an ice cream shop with 3 flavors: vanilla, chocolate, and strawberry. It's easy to quickly pick your favorite, but now imagine there are 50 flavors. Suddenly, you have to weigh dozens of factors. Do you want something fruity or chocolatey? Should you try something new or stick with a classic? The sheer number of options makes it harder to decide, and you may end up leaving without choosing anything. 2. Anticipated regret. Another reason too many choices can make us unhappy is anticipated regret. When there are many options, we tend to worry about making the wrong choice, which can prevent us from enjoying the decision we ultimately make. For example, after buying a pair of shoes, you might start wondering if a different pair would have been more comfortable or better looking. The more options there were, the more likely you are to second-guess your decision, leading to dissatisfaction. 3. Opportunity cost. When we make a decision, we implicitly give up the other options we didn't choose. The more options there are, the greater the opportunity cost, the feeling that we're missing out on something better. This can diminish our satisfaction with the choice we did make, as we focus on what we might have lost rather than what we gained. In economics, opportunity cost is a key concept that helps explain why having too many choices can lead to dissatisfaction. When there are only a few options, the cost of not choosing the others is low. But when there are hundreds of options, the perceived cost of missing out on something better becomes much higher. 4th, escalation of expectations. Having more choices raises our expectations about the outcome. We assume that with so many options, there must be a perfect choice out there. When reality inevitably falls short of these heightened expectations, we feel disappointed. Example: imagine you're buying a smartphone, and there are only 2 models to choose from. You pick one, and it's decent, no complaints. But if you have 50 models to choose from, you expect to find one that's perfect in every way. Even if the phone you choose is objectively better than the two original options, you're more likely to feel let down because it didn't meet your inflated expectations. The paradox of choice has far-reaching implications for various aspects of modern life, from consumer behavior to mental health, relationships, and even societal well-being. 1. Consumerism and the illusion of freedom. In modern society, we're constantly bombarded with choices: what to buy, what to eat, where to live, which career to pursue, and so on. On the surface, this abundance of options seems like a good thing. It represents freedom, autonomy, and individuality. But as Schwartz pointed out, too much choice can lead to dissatisfaction rather than fulfillment. This raises philosophical questions about the nature of freedom. Is having more choices always better, or can it be a burden? Ancient philosophers like Socrates and Buddha argued that true happiness comes not from external abundance, but from inner contentment. The paradox of choice suggests that constantly seeking the best option might make us less happy than simply being content with what we have. 2. Mental health, anxiety, stress, and decision fatigue. The paradox of choice also has significant implications for mental health. Studies have shown that excessive choice can lead to anxiety, stress, and decision fatigue. Decision fatigue occurs when making many choices in a short period depletes our mental energy, leading to poor decision-making and increased stress. This phenomenon is especially relevant in today's fast-paced, consumer-driven world, where people are constantly faced with decisions, from what to wear in the morning to what to watch on Netflix at night. 3. Relationships and social media. The paradox of choice can also apply to relationships, particularly in the age of online dating. With dating apps offering seemingly endless options, people may struggle to commit, always wondering if there's someone better out there. This can lead to a phenomenon known as maximizing, constantly seeking the best possible option rather than being satisfied with a good one. Similarly, on social media, the constant exposure to curated images of other people's lives can create a sense of dissatisfaction as we compare our choices to the idealized versions of reality presented online. The paradox of choice challenges the modern belief that more options lead to greater happiness. While having some degree of choice is essential for autonomy and well-being, too much choice can be overwhelming, leading to anxiety, regret, and dissatisfaction. As you navigate the countless decisions of daily life, consider this: is it always better to have more choices, or is it sometimes wiser to simplify and focus on what truly matters? Perhaps true freedom isn't found in endless options, but in learning to be content with the choices we make. In a world of infinite possibilities, the greatest paradox may be that less is often more. Schrödinger's paradox, heap paradox. When does a pile of sand become a heap? Imagine you have a single grain of sand. Clearly, it's not a heap, it's just one grain. Now you add another grain. Still, it's not a heap. You continue adding grains one by one. Eventually, you have a pile of sand in front of you that anyone would call a heap. But here's the problem. At what exact point did that collection of grains of sand become a heap? Was it after the 10th grain, the 100th, the 1000th? This seemingly simple question is at the heart of the Schrödinger's paradox, also known as the heap paradox. It reveals a profound issue with how we use language, make classifications, and understand concepts in a world full of vagueness and ambiguity. Let's explore the origins of this paradox, break it down with relatable examples, and consider its implications for logic, philosophy, and everyday life. The term Schrödinger comes from the ancient Greek word soros, meaning heap. The paradox was first formulated by the ancient Greek philosopher Eubulides of Miletus, who was a contemporary of Aristotle. Eubulides is credited with several famous paradoxes, including the liar paradox, this statement is false, and the horned paradox, have you lost your horns? His paradoxes were designed to challenge the assumptions of classical logic and force people to confront the limitations of language and reasoning. The Schrödinger's paradox is one of the earliest and most enduring examples of a vagueness paradox. It arises when we try to apply precise logic to vague concepts, terms like heap, bald, tall, or rich, which lack clear boundaries. To fully grasp the Sorite's paradox, let's examine it in a few different contexts. 1. The heap of sand. As mentioned in the introduction, the classic version of the paradox involves a heap of sand. You start with a single grain of sand, which clearly isn't a heap. You add one grain at a time, but no individual grain seems to be the one that transforms the pile into a heap. This leads to two conflicting conclusions. Premise 1, a single grain of sand is not a heap. Premise 2, adding one grain of sand to something that isn't a heap will not make it a heap. Conclusion, therefore, no matter how many grains of sand you add, it will never become a heap. Clearly, this conclusion is absurd because we know that large piles of sand can indeed be called heaps. The paradox arises because there's no precise point at which we can say, this is now a heap. The concept of a heap is inherently vague. 2. The bald man. Another popular version of the Sorite's paradox involves baldness. Imagine a man with a full head of hair. If you remove a single hair, he's obviously not bald. Remove another hair, and he's still not bald. You can keep removing individual hairs, but at no point can you definitively say, this is the exact moment he became bald. Yet, if you remove enough hairs, he will clearly be bald. The paradox reveals that terms like bald are inherently vague. There's no sharp boundary between bald and not bald. This lack of clear boundaries is what makes the paradox so challenging. 3. Wealth and poverty. The Sorite's paradox can also be applied to wealth. Imagine a person with $0. Clearly, they're not rich. If you give them $1, they're still not rich. You can continue adding dollars one by one, but at no point can you definitively say, this is when they became rich. Nevertheless, if you keep adding dollars, they'll eventually have enough money to be considered wealthy. Once again, the paradox arises because terms like rich and poor are vague, with no clear dividing lines. The Sorite's paradox isn't just an intellectual puzzle. It has significant implications for how we think about language, logic, science, and even human behavior. 1. The problem of vagueness in language. One of the key lessons of the Sorite's paradox is that many of the concepts we use in everyday life are inherently vague. Words like heap, bald, tall, and rich don't have precise definitions with clear boundaries. Instead, they exist on a spectrum, where small changes don't lead to sudden shifts in meaning. This vagueness can lead to problems in communication, decision-making, and even legal reasoning. For example, in law, legal terms like reasonable doubt or negligence are often vague, leading to debates and differing interpretations in court cases. In medicine, diagnosing certain conditions can involve vague criteria. For instance, when does high blood pressure become hypertension? There's no sharp dividing line. It's a matter of degree. In ethics, concepts like harm and fairness can be vague, leading to disagreements about what actions are morally acceptable. 2. The Sorite's paradox and fuzzy logic. Classical logic operates on the principle of bivalence, meaning that every statement is either true or false. However, the Sorite's paradox shows that this binary approach doesn't work well for vague concepts. To address this problem, philosophers and computer scientists have developed fuzzy logic, a system in which truth values can exist on a spectrum between 0 and 1. In fuzzy logic, instead of saying this pile is either a heap or not a heap, we can assign a degree of heapness to the pile where 0 represents no heap at all and 1 represents a definite heap. This approach allows us to handle vagueness in a more nuanced way. Fuzzy logic has practical applications in areas such as artificial intelligence. Fuzzy logic is used in AI systems to handle imprecise data and make decisions in uncertain environments. Control systems. Many modern appliances, such as washing machines and air conditioners, use fuzzy logic to optimize their performance based on varying conditions. 3. The Sorite's paradox and human cognition. The Sorite's paradox also sheds light on how the human mind categorizes the world. Our brains are wired to create categories: heap versus not a heap, bald versus not bald, even when reality exists on a continuum. This categorical thinking helps us navigate the world efficiently, but it can also lead to oversimplifications and misunderstandings. For example, when we think about social issues like poverty or inequality, we often use vague categories like rich and poor. But these categories don't capture the full complexity of economic reality, where wealth exists on a spectrum. Recognizing the vagueness of these terms can help us approach such issues with greater nuance and empathy. The Sorites paradox challenges us to rethink how we use language, make classifications, and understand the world. It reveals that many of the concepts we take for granted, like heap, bald, and rich, are inherently vague with no clear boundaries. As you reflect on the Sorites paradox, consider this. In a world full of ambiguity, can we ever truly draw clear lines between categories? Or are all distinctions ultimately matters of degree? Perhaps the true lesson of the Sorites paradox is that while categories help us make sense of the world, reality itself is often more fluid and complex than our language and logic can capture. So, the next time you find yourself wondering when a pile becomes a heap, or when someone becomes rich or bald, remember, it's not about finding the exact dividing line, it's about embracing the ambiguity and complexity of the world around us. Tolerance paradox. Can a tolerant society tolerate intolerance? Imagine living in a society that prides itself on its tolerance, one where freedom of speech, belief, and expression are cherished values. In such a society, people are free to express even controversial or unpopular ideas. But what happens when some of those ideas promote intolerance, hatred, or even the destruction of the very values that allow such freedom? Should society tolerate these intolerant views in the name of tolerance? Or does doing so risk undermining the very foundation of a tolerant society? This dilemma, known as the tolerance paradox, challenges us to confront a fundamental question. How far should tolerance go? And when does it become dangerous to tolerate intolerance? Let's explore the origins of this paradox, break down its implications, and consider its relevance in today's world, where questions of free speech, hate speech, and social harmony are more pressing than ever. The tolerance paradox was first articulated by the Austrian-British philosopher Karl Popper in his 1945 book, The Open Society and Its Enemies. Popper, writing in the aftermath of World War II and the rise of totalitarian regimes like Nazi Germany, was deeply concerned with the survival of open, democratic societies. He recognized that while tolerance is a cornerstone of a free and open society, unchecked tolerance could lead to the rise of intolerant ideologies that seek to destroy that very freedom. Popper famously wrote, "Unlimited tolerance must lead to the disappearance of tolerance. If we extend unlimited tolerance even to those who are intolerant, if we are not prepared to defend a tolerant society against the onslaught of the intolerant, then the tolerant will be destroyed, and tolerance with them." In essence, Popper argued that a truly tolerant society must be willing to limit tolerance in certain cases, to prevent intolerant forces from taking over and eroding the freedoms that tolerance provides. To understand the tolerance paradox, we need to break down its central question. Should a tolerant society tolerate intolerance? And if so, to what extent? Let's examine the paradox through a few simple analogies and scenarios. 1. The debate analogy. Imagine a public debate where all viewpoints are welcome. People with differing opinions engage in respectful discussion, exchanging ideas and learning from one another. Now, suppose a group of speakers arrives who openly reject the rules of respectful discourse. Instead of engaging in debate, they shout down opposing viewpoints, spread hateful rhetoric, and attempt to silence others. If the organizers allow this behavior to continue unchecked, the debate will collapse into chaos, and meaningful dialogue will become impossible. In this case, tolerating the intolerant disrupts the very conditions that make tolerance possible. 2. The garden analogy. Consider a garden with a diverse array of plants. The gardener wants to encourage growth and diversity, so they allow all kinds of plants to grow freely. However, if invasive species, like weeds, are allowed to spread unchecked, they can choke out the other plants, eventually turning the garden into a barren patch dominated by a few aggressive species. In this analogy, the weeds represent intolerant ideologies. Just as the gardener must occasionally remove weeds to protect the diversity of the garden, a tolerant society may need to restrict intolerant forces to preserve freedom and diversity. 3. The legal framework analogy. Most democratic societies have legal frameworks that protect free speech and expression. However, these same societies often impose limits on speech that incites violence, hatred, or discrimination. For example, while people are free to express unpopular opinions, they cannot legally incite others to commit harm or violence against a group. This legal balancing act reflects the tolerance paradox. Societies must draw a line between permissible dissent and dangerous intolerance. The challenge lies in determining exactly where that line should be drawn. The tolerance paradox isn't just a theoretical puzzle. It has real-world implications for how we navigate issues of free speech, hate speech, and social cohesion in a diverse society. 1. Free speech versus hate speech. One of the most contentious issues related to the tolerance paradox is the debate over free speech. In democratic societies, free speech is considered a fundamental right. However, when speech crosses the line into inciting hatred, violence, or discrimination, it raises the question, should such speech be tolerated in the name of free expression? Popper's argument suggests that tolerating hate speech can undermine the very freedoms that free speech is meant to protect. Allowing hateful ideologies to spread unchecked can lead to the erosion of democratic values, as has happened in various historical contexts, such as the rise of fascism in the 20th century. Many countries have grappled with this dilemma by enacting laws that limit hate speech while protecting free expression. For example, in Germany, where the memory of Nazi propaganda remains fresh, laws against Holocaust denial and incitement to hatred are strictly enforced. In the United States, free speech is broadly protected under the First Amendment, but speech that incites violence or constitutes a direct threat is not protected. The challenge lies in finding the right balance. How do we protect free speech while preventing the spread of harmful, intolerant ideologies? 2. Social media and the spread of intolerance. In the digital age, the tolerance paradox has taken on new urgency with the rise of social media platforms. These platforms allow for unprecedented levels of communication and expression, but they've also become breeding grounds for hate speech, misinformation, and extremist ideologies. Social media companies face a version of the tolerance paradox. If they allow all speech, including hate speech, their platforms can become toxic environments that drive users away and harm social cohesion. If they regulate content too strictly, they risk being accused of censorship and infringing on free speech. The solution isn't simple. Platforms like Facebook, Twitter, and YouTube have experimented with various approaches, from content moderation to outright bans of certain groups. However, these efforts have sparked ongoing debates about who gets to decide what is intolerant and how to balance free expression with social responsibility. The rise of populism and extremism. In recent years, many countries have seen a rise in populist and extremist movements that reject democratic norms and promote exclusionary ideologies. These movements often use the language of free speech to justify their actions, arguing that any attempt to restrict them is an attack on freedom. Popper's tolerance paradox suggests that democratic societies must be vigilant in defending themselves against such threats. This doesn't mean suppressing dissent or unpopular opinions, but rather drawing a line when those opinions seek to undermine democracy itself. The tolerance paradox forces us to confront a difficult question. How can we protect the values of tolerance, freedom, and diversity in a world where some people seek to destroy them? While Popper's solution, limiting tolerance for the intolerant, offers a compelling answer, it also raises challenges about who gets to decide what constitutes intolerance and how to enforce such limits fairly. As you reflect on the tolerance paradox, consider this. Is there a way to create a truly tolerant society without risking its collapse into chaos or authoritarianism? Perhaps the answer lies not in finding a perfect balance, but in remaining vigilant, open-minded, and willing to adapt as we navigate the ever-changing landscape of freedom, tolerance, and social harmony. In the end, the tolerance paradox reminds us that tolerance isn't just about accepting differences. It's about protecting the conditions that make acceptance possible, even when that means drawing difficult lines. Friendship paradox. Why do your friends seem more popular than you? Have you ever scrolled through social media and thought, why does everyone seem to have more friends, more exciting lives, and more popularity than I do. You might chalk it up to an illusion, a trick of perception. But what if I told you that this isn't just a subjective feeling, it's a statistical reality? According to the friendship paradox, your friends are likely to have more friends than you on average. This paradox reveals something surprising about how social networks work and has profound implications for how we perceive ourselves, compare ourselves to others, and even how we understand social influence. Let's explore the origins of the friendship paradox, break it down with simple examples, and consider what it means for our mental health, social interactions, and the way we navigate the increasingly interconnected world. The friendship paradox was first described in 1991 by sociologist Scott L. Feld, who discovered an interesting statistical quirk in social networks. When he analyzed various networks, he noticed that, on average, most individuals had fewer friends than their friends did. This finding seemed counterintuitive. After all, shouldn't your number of friends be typical of the people around you? Yet, Feld's analysis showed that your friends are likely to be more popular than you, and this result holds true across a wide range of networks, from school cliques to online social platforms. To understand why this happens, we need to delve into social network theory, which studies how individuals, nodes, are connected by relationships, edges. In any given network, some individuals are more connected than others. These highly connected individuals are called hubs. Because hubs have so many connections, they are disproportionately likely to be your friend, simply because they are connected to so many people. The friendship paradox can be explained through a combination of statistical bias and the structure of social networks. Let's break it down step by step. 1. Understanding social networks. Imagine a small social network where each person represents a node, and a friendship between two people represents an edge connecting them. Some people in this network might have just a few friends, while others have many. The key insight is that individuals with many friends are more likely to appear in other people's social circles simply because they have more connections. 2. Statistical bias. The role of hubs. To illustrate the statistical bias at play, consider this simple analogy. Suppose you have a classroom of 20 students, and most students have 3 or 4 friends. However, there's one particularly popular student, Alex, who has 15 friends. Because Alex is connected to so many people, many of the students in the class are likely to list Alex as a friend. As a result, when you ask each student to count how many friends their friends have, Alex's large friend count will skew the average upward. This is the essence of the friendship paradox. People with many connections are overrepresented in the social circles of others, making it seem like your friends are more popular than you on average. 3. A mathematical perspective. Mathematically, the paradox can be explained by the degree distribution of a network. In a social network, the degree of a node represents the number of connections or friends it has. If we calculate the average degree of all nodes, individuals, we get the average number of friends per person. However, when we calculate the average degree of a node's neighbors, we find that this number is higher than the average degree of the network itself. This discrepancy arises because individuals with more connections contribute more heavily to the average degree of neighbors. In other words, popular people are disproportionately represented in the social circles of others, skewing the perception of popularity. The friendship paradox isn't just a quirky statistical result. It has real-world implications for how we perceive ourselves and our social environments. Let's explore some of these implications in detail. 1. The illusion of popularity and social comparison. One of the most significant impacts of the friendship paradox is how it fuels social comparison. When people perceive that their friends are more popular, more social, or leading more exciting lives, it can lead to feelings of inadequacy, loneliness, and even depression. This effect is amplified in the age of social media, where people are constantly exposed to curated versions of their friends' lives. Because social media platforms tend to highlight highly connected individuals, influencers, celebrities, and popular users, the perception that everyone is more popular than me becomes even more pronounced. Numerous studies have shown that upward social comparison, comparing ourselves to people we perceive as better off, can negatively impact self-esteem and mental well-being. The friendship paradox offers a statistical explanation for why these comparisons may feel so pervasive. the structure of social networks naturally skews our perception of others' popularity. 2. Social influence and the spread of ideas. The friendship paradox also has important implications for social influence and the spread of ideas, behaviors, and information. In social networks, highly connected individuals, hubs, play a crucial role in spreading trends, memes, and even diseases. Because the friends of any given individual are likely to include these hubs, people are more likely to be exposed to new ideas, trends, and behaviors through their social networks. This helps explain phenomena like viral marketing and the rapid spread of memes. Highly connected individuals act as amplifiers, ensuring that information reaches a wide audience quickly. However, this also means that misinformation and harmful behaviors can spread just as rapidly. Understanding the friendship paradox can help us develop better strategies for promoting positive behaviors and countering the spread of harmful content. 3. Inequality in social networks. The friendship paradox highlights a form of inequality in social networks. Some individuals are much more connected than others, and this inequality affects how we perceive social life. Highly connected individuals have more social capital, meaning they have greater access to information, resources, and influence. This inequality can have significant social and economic consequences. For example, in professional networks, highly connected individuals are more likely to hear about job opportunities, receive recommendations, and advance in their careers. Understanding the structure of social networks can help policymakers and organizations design interventions to promote greater equity and inclusion. The friendship paradox challenges our assumptions about social life, popularity, and connection. It reveals that our perception of others is shaped not just by subjective bias, but by the very structure of the networks we inhabit. In a world increasingly driven by social media and digital connectivity, understanding this paradox can help us navigate the complex dynamics of modern social life with greater awareness and empathy. As you reflect on the friendship paradox, consider this. How much of our perception of others is shaped by reality, and how much is shaped by the networks we move in? Perhaps the key to a healthier relationship with social life isn't to compare ourselves to others, but to recognize that the illusion of popularity is built into the fabric of social networks. In a world where connections define our experiences, the friendship paradox invites us to question what we value in our relationships, and to remember that paradoxically, feeling less connected doesn't mean we're alone. Banach-Tarski paradox. How can you cut a ball into pieces and reassemble it into two balls of the same size? Imagine holding a solid sphere, like a rubber ball, in your hand. Now, what if I told you that you could cut this ball into a finite number of pieces, rearrange those pieces, and somehow end up with two identical balls of the same size as the original? It sounds impossible, almost like magic. After all, how can you double the volume of something without adding any extra material? This mind-bending idea isn't a trick or a misunderstanding. It's a real result in mathematics known as the Banach-Tarski paradox. It's one of the most counterintuitive and fascinating paradoxes in all of mathematics, challenging our very understanding of space, volume, and infinity. Let's explore how this paradox works, the mathematical principles behind it, and what it reveals about the strange nature of the universe. The Banach-Tarski paradox was first proposed by two Polish mathematicians, Stefan Banach and Alfred Tarski, in 1924. Their work was part of a broader exploration of set theory and the properties of infinite sets, inspired by the groundbreaking work of Georg Cantor on infinity. At its core, the Banach-Tarski paradox relies on several key mathematical concepts. 1. The axiom of choice, a controversial and powerful principle in set theory that allows for the selection of elements from an infinite number of sets, even when there's no explicit rule for making the selection. 2. Non-measurable sets. In mathematics, most familiar shapes and objects have a well-defined volume or measure. However, the paradox relies on constructing sets that cannot be assigned a meaningful volume. Third group theory. The paradox uses properties of rotations and translations in three-dimensional space, which form a mathematical structure known as a group. While the Banach-Tarski paradox seems to violate basic intuition about volume and conservation of matter, it operates entirely within the framework of abstract mathematics, where space is treated as an infinite collection of points rather than a continuous physical object. To understand how the Banach-Tarski paradox works, let's break it down step by step, using simple analogies and explanations. 1. Cutting the ball into pieces. The paradox begins by imagining a solid sphere in three-dimensional space. The goal is to divide this sphere into a finite number of pieces, specifically 5 pieces, and then rearrange these pieces to form 2 spheres identical in size to the original. However, these aren't ordinary pieces. Unlike the pieces of a puzzle or chunks of a physical object, the pieces in the Banach-Tarski paradox are infinitely complex, meaning they consist of an infinite number of points arranged in a highly intricate, non-continuous way. Each piece is formed using the axiom of choice, which allows for the selection of individual points from different regions of the sphere in a manner that defies conventional geometry. 2. Rearranging the pieces. Once the sphere is divided into 5 non-measurable sets, these pieces are rotated and translated in space without being stretched or altered in size. Remarkably, after this rearrangement, the pieces come together to form 2 spheres of the same size as the original. The key to this result lies in the properties of infinity. While the pieces have no well-defined volume in the traditional sense, they can be manipulated in such a way that they expand into 2 full-size spheres. This works because the sphere is made up of an infinite number of points, and infinity behaves very differently from finite quantities. 3. Why doesn't this work in real life? At this point, you might be wondering, why can't we perform the Banach-Tarski paradox in the real world? The reason lies in the difference between mathematical space and physical space. In mathematics, a sphere is an abstract object made up of infinitely many points with no physical size. In contrast, physical objects are made of atoms, which are discrete and finite. The paradox relies on dividing the sphere into infinitely complex, non-measurable sets, something that's impossible to do with real physical matter. Additionally, the axiom of choice, while accepted in many branches of mathematics, is highly abstract and has no direct physical counterpart. It allows for operations that can't be performed in the real world, where every action must follow the laws of physics. The Banach-Tarski paradox isn't just a mathematical curiosity, it has profound philosophical and scientific implications. Let's explore a few of these implications. 1. The nature of infinity. One of the most striking aspects of the Banach-Tarski paradox is how it highlights the strange properties of infinity. In our everyday experience, adding something to a finite object increases its size. However, in the realm of infinity, such rules no longer apply. The paradox shows that infinite sets can be manipulated in ways that defy conventional logic, leading to results that seem impossible from a finite perspective. This challenges our intuitive understanding of space, volume, and even reality itself. If space can be divided and reassembled in such bizarre ways in the mathematical world, what does that say about the true nature of the universe? Is space fundamentally continuous, or is it made up of discrete points that can be rearranged in infinite ways? 2. The axiom of choice and its controversy. The Banach-Tarski paradox relies heavily on the axiom of choice, a principle that has long been a source of debate among mathematicians. While the axiom is useful for proving many results in set theory, it also leads to counterintuitive conclusions like the Banach-Tarski paradox. Some mathematicians accept the axiom of choice as a valid part of mathematics, while others question its legitimacy, arguing that it allows for constructions that have no physical meaning. The paradox serves as a powerful example of how different axioms can lead to radically different mathematical worlds, raising questions about the nature of mathematical truth. 3. Implications for physics and cosmology. While the Banach-Tarski paradox doesn't apply directly to the physical world, it has inspired philosophical discussions about the nature of space and time in physics. In quantum mechanics and cosmology, there are ongoing debates about whether space is continuous or discrete at the smallest scales. Some theories, such as loop quantum gravity, suggest that space is made up of tiny, indivisible units, similar to how matter is made up of atoms. If space is discrete, the kinds of manipulations described in the Banach-Tarski paradox might not be possible in the real world. However, if space is truly continuous, the paradox raises intriguing questions about what might be possible in a universe governed by infinite sets and the axiom of choice. The Banach-Tarski paradox challenges us to rethink everything we thought we knew about space, volume, and infinity. It shows that in the abstract world of mathematics, our intuitive notions of size and conservation break down, leading to results that seem impossible yet are mathematically valid. As you reflect on this paradox, consider this. What other seemingly impossible results might lie hidden in the abstract realms of mathematics and physics? Perhaps the Banach-Tarski paradox is a reminder that the universe is far stranger and more complex than we can imagine, and that sometimes the most mind-bending ideas arise not from science fiction, but from the pure logic of mathematics. Zeno's paradoxes. Can you ever reach a destination if you have to cover half the distance infinitely many times? Imagine you're standing at the starting line of a race. The finish line is 100 meters away. To reach it, you first have to cover half the distance, 50 meters. Then you must cover half of the remaining distance, 25 meters. After that, you have to cover half of the next remaining distance, 12.5 meters, and so on. Every time you get closer, there's still another half to go. According to this line of reasoning, you would never actually reach the finish line, because there would always be some smaller distance left to cover. This puzzling thought experiment is one of Zeno's paradoxes, and it has fascinated and frustrated philosophers, mathematicians, and scientists for centuries. How can motion and progress be real if, according to logic, they seem impossible? Let's dive into Zeno's paradoxes, break them down, and explore what they reveal about infinity, time, and space. The paradoxes we now associate with Zeno of Elea, a Greek philosopher from the 5th century BCE, were designed to challenge the prevailing ideas about reality and motion. Zeno was a student of Parmenides, another Greek philosopher who believed that change and motion were illusions. Parmenides argued that reality is unchanging, and that all apparent change is a mere illusion of perception. Zeno, in defense of his teacher's ideas, devised a series of paradoxes to show that motion, as commonly understood, leads to logical contradictions. These paradoxes weren't merely philosophical exercises. They touched on profound questions about the nature of space, time, and infinity that wouldn't be fully addressed until the development of modern calculus by Isaac Newton and Gottfried Wilhelm Leibniz over 2,000 years later. Zeno proposed several paradoxes, but the most famous ones are Achilles and the tortoise, the dichotomy paradox, and the arrow paradox. Let's break each of them down in simple terms. 1. Achilles and the tortoise. In this paradox, the swift Greek hero Achilles races against a tortoise. To make the race fair, the tortoise is given a head start. Zeno argues that Achilles can never overtake the tortoise because by the time Achilles reaches the point where the tortoise started, the tortoise will have moved a little further ahead. When Achilles reaches that new point, the tortoise will have moved again, and so on. Even though Achilles is faster, this process repeats infinitely, so Achilles can never catch the tortoise. He's always playing catch-up. Intuitive breakdown. At first glance, this paradox seems absurd because we know from experience that faster runners overtake slower ones. The flaw in Zeno's reasoning lies in the fact that he divides the race into an infinite number of steps, each of which takes less and less time. While the number of steps is infinite, the total time required is finite, meaning Achilles will indeed overtake the tortoise after a finite amount of time. The dichotomy paradox. The dichotomy paradox asks, can you ever reach a destination if you have to cover half the remaining distance infinitely many times? According to Zeno, before you can reach your destination, you must first cover half the distance. Once you've done that, you must cover half of the remaining half, and then half of what's left after that, and so on. Since there are infinitely many halves to cover, Zeno concludes that motion is impossible because you can never complete an infinite number of tasks. Intuitive breakdown. This paradox highlights the idea of infinite division. While it's true that the distance can be divided into infinitely many parts, the sum of these parts converges to a finite value. For example, if the total distance is 1 unit, the sum of 1/2 plus 1/4 plus 1/8 plus adds up to exactly 1. Modern calculus, through the concept of limits, resolves this paradox by showing that an infinite series can have a finite sum, The arrow paradox. In the arrow paradox, Zeno argues that if you observe an arrow in flight at any single instant in time, it appears motionless. It occupies a fixed position in space. Since time is composed of a series of such instants, and the arrow is motionless at each instant, it must be motionless for the entire duration of its flight. Therefore, Zeno concludes, motion is an illusion. Intuitive breakdown. This paradox arises from the idea that time can be broken down into discrete, indivisible moments. However, in modern physics and mathematics, we understand time as a continuous flow, not a sequence of frozen instants. Motion is defined as a change in position over time, and calculus provides the tools to describe how an object moves through a continuum of time. Zeno's paradoxes may seem like simple word games, but they raise profound questions about the nature of reality, space, and time. Let's explore some of the key philosophical and mathematical implications. 1. The concept of infinity. At the heart of Zeno's paradoxes is the concept of infinity. Zeno's arguments show that when we divide space and time infinitely, we encounter logical contradictions. This led to centuries of philosophical debate about whether infinity exists in the real world or is merely a mathematical abstraction. It wasn't until the development of calculus in the 17th century that mathematicians found a way to rigorously handle infinity. By introducing the concept of limits, calculus allows us to sum infinitely many small quantities to arrive at a finite result, resolving the paradoxes mathematically. 2. The nature of space and time. Zeno's paradoxes also challenge our understanding of space and time. Are space and time continuous, meaning they can be divided infinitely, or are they discrete, composed of tiny, indivisible units? This question remains open in modern physics. In classical physics, space and time are treated as continuous, meaning they can be divided infinitely without limit. In quantum physics, some theories, such as loop quantum gravity, suggest that space and time may be discrete at the smallest scales, with a fundamental unit of length known as the Planck length. If space and time are discrete, Zeno's paradoxes might be resolved by showing that infinite division isn't possible beyond a certain point. However, if space and time are truly continuous, we must rely on the mathematical tools of calculus to explain how motion and change occur despite infinite division. 3. Zeno's paradoxes and modern science. Zeno's paradoxes continue to inspire modern science and philosophy. In particular, they highlight the limitations of human intuition when dealing with abstract concepts like infinity and continuity. They also remind us that seemingly simple questions like whether motion is possible can lead to profound insights about the nature of reality. In computer science, Zeno's paradoxes have analogs in algorithms and processes that involve infinite steps or recursive tasks. Understanding how to handle infinite sequences is essential in fields ranging from numerical analysis to artificial intelligence. Zeno's paradoxes challenge us to reconsider our assumptions about motion, space, and time. While modern mathematics and physics provide solutions to these paradoxes, they also reveal the strange and counterintuitive nature of infinity and continuity. As you ponder Zeno's paradoxes, consider this. Is reality truly continuous, or is it composed of discrete, indivisible units? And if infinity is merely a mathematical construct, what does that mean for our understanding of the universe? Perhaps Zeno's true lesson is that the universe is far more complex and mysterious than our everyday experiences suggest, and that the quest to understand it requires us to confront paradoxes that defy intuition, yet point the way to deeper truths. The Sleeping Beauty paradox. What's the probability that you're living through a specific moment? Imagine being part of a strange experiment. On Sunday night, you're put to sleep, and while you're unconscious, a coin is flipped. If it lands heads, you're woken up once. On Monday, if it lands tails, you're woken up twice, on both Monday and Tuesday. But after waking up on Monday, your memory is erased so that you have no recollection of it when you wake up again on Tuesday. Each time you wake up, you have no idea what day it is or what the result of the coin flip was. Now here's the question. When you wake up, what's the probability that the coin landed heads? This seemingly simple question has led to one of the most intriguing and controversial puzzles in probability theory, known as the Sleeping Beauty paradox. Let's explore how this paradox works, why it's so puzzling, and what it reveals about our understanding of probability, time, and self-awareness. The Sleeping Beauty paradox was first introduced by philosopher Arnold Zuboff in 1989 and later popularized by Adam Elga in 2000. It's named after the famous fairy tale character Sleeping Beauty, because, like the character, the participant in the paradox is put to sleep and woken up under unusual circumstances. However, unlike the fairy tale, the paradox isn't about magic. It's about probability and how we reason about events when our knowledge is incomplete or uncertain. At first glance, the problem seems straightforward. A coin is flipped, and based on the outcome, Sleeping Beauty is woken up either once, if heads, or twice, if tails. But because her memory is erased after each awakening, she can't distinguish between waking up on Monday or Tuesday. This creates a puzzle. When she wakes up, how should she assess the likelihood that the coin landed heads? Philosophers and mathematicians have proposed two main answers to this question. 1. The 1/2 answer. Some argue that the probability of heads is 1/2 because the coin flip is a fair event, and the fact that Sleeping Beauty is woken up doesn't change the underlying probability of the coin landing heads or tails. 2. The 1/3 answer. Others argue that the probability of heads is 1/3 because there are 3 possible awakenings. 1 on Monday if heads, and 2, Monday and Tuesday if tails. Since Sleeping Beauty doesn't know which awakening she's experiencing, she should assign equal probability to each, resulting in a 1/3 chance for heads. To fully understand the Sleeping Beauty paradox, let's break down the two main interpretations and their reasoning. 1. The 1/2 argument. Coin flip as a fair event. Those who argue that the probability of heads is 1/2 base. They're reasoning on the idea that the coin flip is a fair event. Before the experiment begins, Sleeping Beauty knows that the coin has an equal chance of landing heads or tails. Nothing about the process of being woken up or having her memory erased changes the fairness of the coin flip itself. When Sleeping Beauty wakes up, she gains no new information about the coin flip. After all, she knows she would be woken up regardless of whether the coin landed heads or tails. Therefore, according to this argument, the probability of heads remains 1/2 as it was when the coin was originally flipped. 2. The 1/3 argument. Counting possible awakenings. The alternative argument, which concludes that the probability of heads is 1/3, focuses on the number of possible awakenings Sleeping Beauty could experience. If the coin lands heads, there is only 1 awakening on Monday. If the coin lands tails, there are 2 awakenings on Monday and Tuesday. Since Sleeping Beauty can't distinguish between the awakenings on Monday and Tuesday in the tails scenario, she should assign an equal probability to each of the 3 possible awakenings. 1. Awakening on Monday if heads 2. Awakening on Monday if tails 3. Awakening on Tuesday if tails. Each awakening represents a distinct, equally likely scenario. Therefore, the probability of being in the heads scenario, the single awakening, is 1 out of 3, or 1/3. The Sleeping Beauty paradox raises deep questions about how we think about probability, time, and self-awareness. Let's explore some of the key implications. 1. What is probability? One of the core issues in the Sleeping Beauty paradox is how we define probability. There are 2 main interpretations of probability. Objective probability. This refers to the inherent likelihood of an event occurring based on physical laws or randomness. In the case of the Sleeping Beauty paradox, the objective probability of the coin landing heads is 1/2, because the coin flip is fair. Epistemic probability. This refers to the probability assigned based on what an individual knows. From Sleeping Beauty's perspective, the epistemic probability of heads might be 1/3, because she knows she could be in any of the 3 possible awakenings. The paradox illustrates the tension between these 2 interpretations and forces us to question whether probability is purely about the physical world or also about our subjective knowledge of it. 2. Self-location and indexical information. The Sleeping Beauty paradox also raises questions about self-location, the idea of determining where or when you are in the universe. When Sleeping Beauty wakes up, she knows general facts about the experiment. e.g., that a coin was flipped and she would be woken up at least once. But she doesn't know her specific location in time, i.e., whether it's Monday or Tuesday. This idea is related to indexical information that depends on the perspective of the individual, such as "I am here" or "it is now." Philosophers have long debated how to incorporate such information into reasoning and probability. 3. The problem of reference class. Another important issue in the paradox is the problem of defining the reference class, the set of possible scenarios Sleeping Beauty should consider when assigning probabilities. If she considers only the coin flip as the relevant event, she might conclude the probability of heads is 1/2. If she considers each awakening as a separate event, she might conclude the probability of heads is 1/3. The choice of reference class can significantly affect how we reason about probability, and this has implications beyond the paradox. For example, in anthropic reasoning, where we consider our existence in the universe, the reference class problem plays a crucial role in debates about the likelihood of intelligent life and the nature of the cosmos. While the Sleeping Beauty paradox may seem abstract, it has real-world analogies and applications in fields such as decision theory, game theory, and cosmology. 1. Anthropic principle. The paradox is often compared to questions about our place in the universe. If there are infinitely many possible universes, how should we reason about the likelihood of existing in this particular one? 2. Repeated trials. The paradox can be thought of as a problem involving repeated trials or experiments, where memory and self-awareness affect how probabilities are assigned. The Sleeping Beauty paradox challenges us to rethink fundamental concepts of probability, time, and self-awareness. It forces us to ask, is probability an objective feature of the world, or is it something that depends on our perspective and knowledge? As you reflect on this paradox, consider how often we encounter similar puzzles in life, situations where we must make decisions based on incomplete or uncertain information. Perhaps the true lesson of the Sleeping Beauty paradox is that reasoning about the unknown requires not just logic, but also a deep understanding of how our perspective shapes what we know. In the end, the paradox invites us to ponder one of the most profound questions of all. What's the probability that we are living through this specific moment in time? And what does that mean for how we experience the world? Russell's paradox. Can a set contain itself? Imagine you're organizing a massive library with millions of books. Among these, some books contain lists of other books, while others don't. Now, you decide to create a new book that lists all the books that do not list themselves. Here's the twist. Should this new book list itself? If it does, then it violates its own rule because it's supposed to list only books that don't list themselves. But if it doesn't list itself, then it should list itself because it fits the rule of listing books that don't list themselves. This self-referential puzzle creates a logical contradiction, and it's an example of what's known as Russell's paradox. This paradox, discovered by the British philosopher and mathematician Bertrand Russell in 1901, shook the very foundations of mathematics and set theory. It forced mathematicians to rethink how they defined sets, logic, and the structure of formal systems. Let's dive into the paradox, explore its implications, and see how it transformed the landscape of modern mathematics. To understand Russell's paradox, we first need to explore what a set is in mathematics. A set is simply a collection of distinct objects called elements. Sets can contain anything: numbers, letters, shapes, or even other sets. In the late 19th and early 20th centuries, mathematicians, led by Georg Cantor, developed set theory as a rigorous foundation for all of mathematics. Cantor's work on infinity and his theory of sets were revolutionary, but they also introduced new challenges. One of the key ideas was that a set could, in theory, contain anything, even other sets. This led to the question, can a set contain itself as an element? Some sets clearly do not contain themselves. For example, the set of all even numbers doesn't contain itself because it's not an even number, it's a set. However, other sets, such as the set of all sets, seem like they might contain themselves. This is where things start to get tricky. Russell's paradox arises when we consider a specific type of set. Let's define a set RR as the set of all sets that do not contain themselves. Now we ask the crucial question: does RR contain itself? 1. If RR contains itself, then by its definition, it should not contain itself, because it only includes sets that do not contain themselves. 2. If RR does not contain itself, then by its definition, it should contain itself, because it qualifies as a set that does not contain itself. In both cases, we arrive at a contradiction. This self-referential loop creates a paradox because the set RR cannot consistently be defined as either containing itself or not containing itself without violating its own definition. An analogy: the Barber paradox. To make Russell's paradox easier to understand, consider a simpler analogy known as the Barber paradox. Imagine a town with a single barber who shaves all those and only those who do not shave themselves. The question is, does the barber shave himself? If the barber shaves himself, then he violates the rule that he only shaves those who do not shave themselves. But if he doesn't shave himself, then he must shave himself, because he shaves all those who do not shave themselves. Once again, we encounter a logical contradiction, similar to Russell's paradox. Russell's paradox had profound implications for mathematics, logic, and philosophy, forcing mathematicians to confront fundamental questions about how they defined sets and the foundations of their discipline. 1. The crisis in set theory. When Russell discovered his paradox, set theory was considered the bedrock of mathematics. Mathematicians believed they could define all mathematical concepts using sets, providing a rigorous foundation for the entire field. Russell's paradox revealed a serious flaw in this approach. If sets could be defined so broadly, logical contradictions would arise. In response, mathematicians sought ways to avoid such contradictions by restricting how sets could be defined. One of the key solutions was proposed by Ernst Zermelo and later refined by Abraham Fraenkel, resulting in the Zermelo-Fraenkel set theory ZF, which includes specific axioms to prevent paradoxical sets from being formed. One of these axioms, known as the axiom of separation, ensures that sets can only be defined using well-defined properties that avoid self-reference. 2. Type theory and formal logic. Bertrand Russell himself, along with Alfred North Whitehead, attempted to resolve the paradox by developing a new logical system called type theory. In type theory, objects are organized into a hierarchy of types, and sets can only contain elements of a lower type. This prevents sets from containing themselves, thereby eliminating the possibility of self-referential paradoxes. Russell and Whitehead outlined their approach in the monumental work Principia Mathematica, published between 1910 and 1913. Although type theory provided a way to avoid Russell's paradox, it was considered cumbersome and less intuitive than the revised set theory proposed by Zermelo and Fraenkel. 3. Gödel's incompleteness. Theorems. Russell's paradox also had a lasting impact on the philosophy of mathematics, particularly in the work of Kurt Gödel. In 1931, Gödel published his famous incompleteness theorems, which showed that any consistent formal system powerful enough to include arithmetic would inevitably contain true statements that could not be proven within the system. Gödel's work demonstrated that even if mathematicians could avoid paradoxes like Russell's by carefully defining sets and formal systems, there would always be limits to what those systems could achieve. This shattered the dream of a complete, self-contained foundation for mathematics and led to a more nuanced understanding of mathematical truth. 4. Self-reference and paradoxes in other fields. Russell's paradox isn't limited to mathematics. It also appears in other fields, such as computer science, linguistics, and philosophy. In computer science, self-referential paradoxes arise in programming and algorithms. For example, the famous halting problem, introduced by Alan Turing, asks whether a computer program can determine whether another program will halt or run forever. Turing showed that no such general algorithm exists, using reasoning similar to Russell's paradox. In linguistics, self-reference plays a role in paradoxical statements like the liar paradox, where a sentence refers to itself in a way that creates a contradiction, e.g., this sentence is false. In philosophy, Russell's paradox raises questions about the nature of truth, self-awareness, and language. Can we fully describe a system from within the system itself, or do we always risk creating contradictions? Russell's paradox forces us to confront the limits of logic, language, and formal systems. It shows that even in the seemingly precise world of mathematics, paradoxes can arise when we allow for self-reference and infinite sets. In response to this paradox, mathematicians developed more rigorous frameworks for set theory, but the fundamental issues it raises about self-reference and consistency remain relevant in many areas of thought. As you reflect on Russell's paradox, consider this. Are there limits to what we can define and understand using logic? Or is it simply a matter of finding the right system? Perhaps Russell's true lesson is that the pursuit of knowledge always involves navigating paradoxes, and that these paradoxes, rather than being obstacles, are gateways to deeper understanding. Simpson's paradox. How can data trends reverse when combined? Imagine a scenario where two universities are comparing their admission rates for male and female applicants. Each university shows that more females than males are admitted when analyzed individually, yet, when the data from both universities is combined, the trend reverses, and it suddenly appears that more males than females are admitted overall. How can this be? How can a trend observed in separate groups disappear or even reverse when the groups are combined? This puzzling phenomenon is known as Simpson's paradox, a statistical anomaly that reveals how easily data can mislead us, even when the numbers seem clear. Simpson's paradox challenges our understanding of causality, data interpretation, and decision-making, making it a crucial concept in fields ranging from medicine to economics to social science. Let's explore how this paradox works, why it happens, and what it teaches us about the hidden complexities of interpreting data. Simpson's paradox was first described by British statistician Edward H. Simpson in 1951, though earlier versions of the paradox had been discussed by other mathematicians. The paradox arises in situations where data can be divided into groups or categories, and the trends observed within those groups differ from the trend observed when the data is combined. At its core, Simpson's paradox occurs because of confounding variables, factors that influence both the independent and dependent variables in a study. When data is grouped, these confounding variables may obscure or reverse the true relationship between the variables being studied. To understand Simpson's paradox more clearly, let's walk through a few simple examples that illustrate how trends can reverse when data is combined. Example: university admissions consider two universities A and B and their admission rates for male and female applicants. At University A, 90 out of 100 male applicants are admitted, 90% admission rate. 10 out of 20 female applicants are admitted, 50% admission rate. At University B, 30 out of 50 male applicants are admitted, 60% admission rate. 5 out of 10 female applicants are admitted, 50% admission rate. When you look at each university individually, the admission rate for males is higher than for females. However, when we combine the data from both universities, the overall admission rates change. Combined data: O males, 120 applicants, 90 plus 30 equals 120 admitted, 75% admission rate. O females, 30 applicants, 10 plus 5 equals 15, admitted, 50% admission rate. Surprisingly, the overall trend suggests that females have a lower admission rate, even though each university admitted a higher percentage of female applicants than male applicants. This reversal happens because University A had more applicants overall and a higher admission rate for males, skewing the combined data. 2. Example: treatment effectiveness. Another common example of Simpson's paradox occurs in medical studies. Suppose researchers are comparing two treatments, A and B, for a disease. They collect data on how many patients recover under each treatment. In Group 1, mild cases, O treatment A, 90 out of 100 patients recover, 90% recovery rate. O treatment B, 30 out of 100 patients recover, 30% recovery rate. 50 patients recover, 60% recovery rate. In Group 2, severe cases, O treatment A, 10 out of 50 patients recover, 20% recovery rate. O treatment B, 40 out of 100 patients recover, 40% recovery rate. Within each group, treatment A appears more effective for mild cases, while treatment B appears more effective for severe cases. However, when the data is combined, combined data, O treatment A, 100 out of 150 patients recover, 67% recovery rate. O treatment B, 70 out of 150 patients recover, 47% recovery rate. The combined data shows that treatment A is more effective overall despite treatment B being more effective for severe cases. This reversal happens because the proportion of mild to severe cases differs between the two treatments, acting as a confounding variable. Simpson's paradox highlights several important lessons about how we interpret data, reason about causality, and make decisions in complex situations. 1. The danger of aggregating data. One of the key lessons of Simpson's paradox is that aggregating data without considering subgroups can lead to misleading conclusions. In both the university admissions and treatment effectiveness examples, combining data obscured important differences between groups. This has significant implications for research in fields like medicine, economics, and social science. For example, in public health studies, combining data from different demographic groups can hide disparities in outcomes. Similarly, in business, aggregating customer data without considering different segments can lead to flawed marketing strategies. 2. The role of confounding variables. Simpson's paradox illustrates the importance of identifying and controlling for confounding variables. A confounding variable is one that influences both the independent variable, e.g., gender or treatment, and the dependent variable, e.g., admission rate or recovery rate, potentially distorting the relationship between them. In the university example, the overall admission rate was influenced by the different proportions of applicants at each university. In the treatment example, the severity of cases acted as a confounding variable, affecting both the treatment choice and the recovery outcome. Understanding confounding variables is crucial in scientific research, where failing to account for them can lead to incorrect conclusions about cause and effect. 3. Implications for causal inference. Simpson's paradox also raises philosophical questions about causal inference, how we determine whether one thing causes another. The paradox shows that apparent correlations can change or even reverse when data is grouped differently, suggesting that correlation alone is not sufficient to establish causation. To address this issue, researchers use methods like randomized controlled trials and statistical models that account for confounding variables. These methods help ensure that observed relationships reflect true causal effects rather than artifacts of data aggregation. 4. Biases in human reasoning. Simpson's paradox reveals how easily human intuition can be misled by data. Our minds are naturally inclined to look for patterns and draw conclusions, but we often overlook the complexity of underlying factors. This can lead to biases in reasoning, such as confirmation. Bias, interpreting data in a way that confirms our existing beliefs without considering alternative explanations. Oversimplification, ignoring confounding variables or subgroup differences in favor of simple, overarching conclusions. Recognizing these biases is essential for making better decisions in both personal and professional contexts. Real-world applications of Simpson's paradox. Simpson's paradox has real-world applications in various fields. 1. Healthcare. Understanding how treatment outcomes vary across different patient groups can improve medical decision-making and personalized medicine. 2. Economics. Economists use advanced statistical techniques to control for confounding variables when analyzing the effects of policies or interventions. 3. Machine learning. Data scientists must be aware of Simpson's paradox when building predictive models, ensuring that subgroup differences are accounted for. 4th, public policy. Policymakers need to consider subgroup differences when designing and evaluating programs to avoid misleading conclusions about their effectiveness. Simpson's paradox challenges us to think critically about how we interpret data and draw conclusions. It shows that the same set of data can tell different stories depending on how it's grouped and analyzed. In a world where data drives decisions in fields ranging from healthcare to business to public policy, understanding this paradox is more important than ever. As you reflect on Simpson's paradox, consider this. How often do we base our decisions on aggregated data without questioning the underlying factors? Perhaps the true lesson of Simpson's paradox is that data, like life, is rarely as simple as it seems, and that true wisdom lies in recognizing the hidden complexities beneath the surface. Olbers's paradox. If the universe is infinite, why is the night sky dark? Have you ever looked up at the night sky and marveled at its darkness, punctuated by the tiny, twinkling lights of stars scattered across the vast expanse? Now consider this. If the universe is infinite, filled with an infinite number of stars, shouldn't the sky be ablaze with light, shining as brightly as the surface of the sun in every direction? After all, in an infinite universe, every line of sight should eventually end at the surface of a star. Yet, the night sky remains dark. This puzzling observation is known as Olbers's paradox, and it forces us to confront some profound truths about the nature of the universe. Let's explore the history of this paradox, break down why it's so perplexing, and uncover how its resolution led to some of the most important discoveries in modern cosmology, including the Big Bang Theory and the expanding universe. Background context: the origins of Olbers's paradox. Olbers's paradox is named after the German astronomer Heinrich Wilhelm Olbers, who formally described it in 1840–1823. However, the paradox had been pondered by earlier thinkers, including Johannes Kepler in 1610 and Edmund Halley and Jean-Philippe de Chazeau in the 18th century. Olbers is credited with popularizing the paradox and framing it as a serious scientific question. At the time, many scientists believed in a static, infinite universe, one that had always existed and would always continue to exist. In such a universe filled with an infinite number of stars distributed uniformly across space, every line of sight should intersect with the surface of a star. This reasoning implies that the entire sky should be uniformly bright, with no dark regions at all. Yet, contrary to this expectation, the night sky is predominantly dark. This contradiction between theory and observation is what makes Olbers's paradox so intriguing. To understand Olbers's paradox more clearly, let's break it down into a few key ideas. 1. Infinite stars in an infinite universe. Imagine that the universe is infinite in size and filled uniformly with stars. If this is true, then no matter where you look in the sky, your line of sight should eventually hit a star. Even though stars are separated by vast distances, an infinite universe should contain an infinite number of stars. Therefore, the cumulative light from all these stars should make the entire sky glow brightly. To illustrate this, think of standing in a dense forest. No matter which direction you look, your line of sight eventually ends at a tree trunk. Similarly, in an infinite universe, your line of sight should always end at the surface of a star. 2. Diminishing light with distance. One might argue that stars farther away appear dimmer because their light diminishes with distance. While it's true that the intensity of light decreases with the square of the distance, as described by the inverse square law, the total number of stars increases with distance. In an infinite universe, for every distant star that appears dim, there should be many more stars at that same distance. When you sum up the light from all these stars, the sky should still be bright. Mathematically, if the universe is infinite, the total amount of light from stars at all distances should add up to an infinite brightness, resulting in a uniformly lit sky. 3. Why isn't the sky bright? Given the logic above, why isn't the night sky uniformly bright? There must be something fundamentally wrong with the assumptions we're making about the universe. Resolving Olbers's paradox requires us to rethink our understanding of the universe's structure, its age, and the nature of light and time. The resolution of Olbers's paradox involves several key ideas from modern cosmology, including the finite age of the universe, the expansion of space, and the finite speed of light. 1. The finite age of the universe. One of the main reasons the night sky is dark is that the universe has a finite age. According to the Big Bang Theory, the universe began around 13.8 billion years ago. This means that light from stars beyond a certain distance hasn't had enough time to reach us yet. Even if the universe is infinitely large, we can only see as far as light has traveled since the beginning of time. This observable region of the universe is called the observable universe, and it places a limit on how many stars we can see. If the universe were infinitely old, we would indeed expect to see light from an infinite number of stars, leading to a bright sky. But because the universe has a finite age, we only see a finite number of stars, and the gaps between them appear dark. 2. The expansion of the universe. Another crucial factor in resolving Olber's paradox is the expansion of the universe. Discovered by Edwin Hubble in the 1920s, the expansion of the universe means that galaxies are moving away from us, and the farther away they are, the faster they're receding. This expansion causes the light from distant stars and galaxies to be redshifted, stretched to longer wavelengths, making it less energetic and shifting it out of the visible spectrum into the infrared and microwave ranges. As a result, even though there may be countless distant stars, much of their light is no longer visible to us because it has been redshifted beyond the range of human vision. This redshifting effect, combined with the finite age of the universe, explains why the night sky is mostly dark. 3. The cosmic microwave background. Although the night sky appears dark to the human eye, it isn't entirely devoid of light. In fact, the universe is bathed in a faint glow of radiation known as the cosmic microwave background, CMB. This radiation is the afterglow of the Big Bang, and it provides crucial evidence for the universe's hot, dense origins. The CMB is visible in the microwave part of the electromagnetic spectrum, and it represents the cooled remnants of the light that filled the universe when it was only about 380,000 years old. While it isn't visible to the naked eye, sensitive instruments can detect it, revealing that the sky is, in a sense, filled with light, just not in the way Olber is originally imagined. Olber's paradox has far-reaching implications for our understanding of the universe and our place within it. It highlights the importance of questioning our assumptions and using observation to refine our theories about reality. Let's explore some of these implications. 1. The nature of time and space. Olber's paradox forces us to confront the idea that space and time are not infinite in the way once imagined. The finite age of the universe means that time has a beginning, and the expansion of space means that the universe is dynamic, constantly evolving. These ideas are central to modern cosmology and challenge the notion of an eternal, unchanging cosmos. 2. The limits of human perception. The paradox also underscores the limits of human perception. While the night sky appears dark to our eyes, it's actually filled with light across the electromagnetic spectrum. Instruments like radio telescopes reveal a universe teeming with radiation, from the cosmic microwave background to distant galaxies emitting radio waves. This teaches us that our sensory experience of the world is only a small part of the larger reality. The role of science in understanding paradoxes. Olber's paradox is a testament to the power of science to resolve seemingly insoluble puzzles. By questioning assumptions, gathering data, and refining theories, scientists transformed a simple question about the night sky into a profound understanding of the universe's origins, structure, and evolution. Olber's paradox begins with a simple, childlike question: why is the night sky dark? But its resolution reveals some of the deepest truths about the universe. It teaches us that reality is often more complex than it appears, and that answering even the most basic questions can lead to profound discoveries. As you reflect on Olber's paradox, consider this: what other everyday observations might hide deeper truths about the universe? Perhaps the next great scientific breakthrough will come from asking a simple question, just as Olber's did when he looked up at the dark night sky. After all, the greatest mysteries often lie hidden in plain sight, waiting for curious minds to uncover them. Quantum Zeno effect. Can you stop something from happening just by observing it continuously? Imagine watching a kettle of water on a stove. You know from experience that staring at it won't stop it from boiling. No matter how closely you watch, it will eventually reach its boiling point. Now imagine a world where simply observing the water continuously could somehow prevent it from boiling altogether. As bizarre as it sounds, in the realm of quantum mechanics, such a phenomenon does exist. This is known as the quantum Zeno effect, a paradox that reveals how observation can fundamentally alter the behavior of quantum systems. Let's explore the origins of this paradox, break down how it works in simple terms, and dive into its philosophical and scientific implications. To understand the quantum Zeno effect, we first need to delve into one of the strangest principles of quantum mechanics: the role of observation. In classical physics, observation is passive. You can measure a system without fundamentally changing its behavior. For example, you can measure the speed of a car without altering its motion. However, in quantum mechanics, observation plays a much more active role. When we observe a quantum system, we disturb it in a way that affects its future behavior. This idea is closely tied to the concept of wave function collapse. Wave function and collapse. In quantum mechanics, particles like electrons don't have definite positions or velocities until they're measured. Instead, they exist in a superposition of many possible states, described mathematically by a wave function. When you measure the particle, its wave function collapses, forcing the particle to adopt a definite state. This collapse is what gives rise to the strange behavior of quantum systems when observed. The quantum Zeno effect gets its name from Zeno of Elea, a Greek philosopher famous for his paradoxes about motion. One of Zeno's most well-known paradoxes suggests that an arrow in flight is motionless at every single instant in time, implying that motion itself is an illusion. Similarly, the quantum Zeno effect suggests that continuous observation can freeze the state of a quantum system, preventing it from evolving over time. Here's how it works in a simple scenario. 1. A decaying particle. Consider a particle that's unstable. It's in the process of decaying into another particle. If left alone, this decay process follows a well-defined probability over time. After a certain period, there's a high chance the particle will have decayed. However, if we measure the particle repeatedly at very short intervals, something strange happens. The particle seems to freeze in its initial state. Each time we measure it, we force its wave function to collapse back to the original state, effectively resetting the decay process. If we repeat the measurements frequently enough, we can prevent the particle from decaying entirely. This counterintuitive result, that frequent observation can inhibit the natural evolution of a quantum system, is what we call the quantum Zeno effect. 2. Analogies to understand the effect. To make this idea more intuitive, let's use a simple analogy. Imagine you're trying to walk across a room, but every second someone shines a bright light on you and asks, "Are you still at the starting point?" Each time they do this, you have to freeze and answer. Because you're constantly being interrupted, you can't make any progress toward your destination. In a similar way, frequent measurements in a quantum system can prevent it from evolving naturally. Third, mathematical explanation. The quantum Zeno effect can be understood mathematically through the equations that govern quantum systems. The probability of a quantum state transitioning to another state is determined by its time evolution, described by the Schrödinger equation. When measurements are made frequently enough, the time intervals between measurements become so short that the probability of transition approaches zero, effectively freezing the system in its initial state. The quantum Zeno effect has profound implications for both philosophy and science. It challenges our understanding of observation, time, and the nature of reality itself. 1. The nature of observation. In classical physics, observation is a passive act. It involves gathering information without altering the system being observed. The quantum Zeno effect, however, shows that in quantum mechanics, observation is an active process that can fundamentally alter the outcome of events. This raises philosophical questions about the nature of reality. If observation can prevent a quantum system from evolving, does that mean reality itself is dependent on being observed? This idea is closely related to the Copenhagen interpretation of quantum mechanics, which posits that quantum systems don't have definite properties until they're measured. 2. Free will and determinism. The quantum Zeno effect also has implications for debates about free will and determinism. In a classical deterministic universe, the future is predetermined by the laws of physics. However, in a quantum universe, the future is probabilistic. It's governed by probabilities rather than certainties. By showing that observation can alter the behavior of quantum systems, the quantum Zeno effect suggests that the act of observation, an intentional act, can influence the outcome of events. This raises intriguing questions about the role of consciousness in shaping reality. 3. Practical applications. Despite its seemingly paradoxical nature, the quantum Zeno effect has real-world applications in various fields of science and technology. Quantum computing. In quantum computing, the quantum Zeno effect can be used to protect quantum information from decoherence, the loss of quantum coherence caused by interaction with the environment. By frequently measuring or interacting with a quantum system, it's possible to stabilize it and prevent unwanted changes. Nuclear physics. The quantum Zeno effect has been observed in experiments involving unstable particles. By repeatedly measuring the state of a decaying particle, researchers have been able to slow down or even halt the decay process. Biophysics. Some researchers speculate that the quantum Zeno effect might play a role in biological processes, such as photosynthesis, where quantum coherence is believed to enhance the efficiency of energy transfer. Criticism and limitations. While the quantum Zeno effect is a fascinating phenomenon, it's not without its limitations and criticisms. For example, 1. Practical limitations. In practice, it's difficult to perform measurements frequently enough to fully freeze a quantum system. The intervals between measurements must be extremely short, which poses significant technical challenges. 2. Interpretational issues. The quantum Zeno effect is often cited in discussions about the interpretation of quantum mechanics. Different interpretations of quantum mechanics, such as the many worlds interpretation, offer different explanations for why the effect occurs. The quantum Zeno effect challenges our intuition about time, observation, and reality. It shows us that in the quantum world, simply observing something can prevent it from changing, a concept that seems almost magical from a classical perspective. This paradox not only deepens our understanding of quantum mechanics, but also raises profound philosophical questions about the nature of existence. As you reflect on the quantum Zeno effect, consider this. If observation can alter reality at the quantum level, what does that mean for our role as observers in the universe? Perhaps the greatest mystery isn't just how the universe works, but how our awareness of it shapes what we experience. In the end, the quantum Zeno effect reminds us that reality is far stranger than it appears, and that the act of observing the world might be more powerful than we ever imagined. Time reversal paradox. Why can't we rewind time even though the laws of physics allow it? Imagine watching a video of a glass falling off a table, shattering into countless pieces on the floor. Now imagine playing the video in reverse. The broken glass reassembles perfectly, leaps back onto the table, and stands upright. While this reverse scenario seems absurd in real life, the strange thing is that it doesn't violate any fundamental laws of physics. The equations governing the motion of particles are time reversible. They work just as well backward as they do forward. So why don't we ever see shattered glasses spontaneously reassembling? Why does time seem to flow in only one direction? This puzzling question lies at the heart of the time reversal paradox, a paradox that forces us to confront the asymmetry of time in a universe governed by time-symmetric physical laws. Let's explore the origins of this paradox, understand its connection to entropy and the arrow of time, and consider what it tells us about the nature of reality. To understand the time reversal paradox, we first need to grasp two key concepts: time symmetry and the arrow of time. First, time symmetry in physics. In classical and quantum physics, many fundamental laws are time symmetric. This means that if you reverse the direction of time in the equations, they remain valid. For example, Newton's laws of motion, Maxwell's equations for electromagnetism, and even the Schrödinger equation in quantum mechanics are time reversible. If you were to rewind the motion of particles described by these equations, the behavior would still make perfect sense from a purely mathematical perspective. In other words, the fundamental laws of physics don't seem to prefer a particular direction of time. They treat the past and the future symmetrically. 2. The arrow of time and entropy. Despite the time symmetry of physical laws, we experience time as moving in one direction, forward. This one-way flow of time is what we call the arrow of time. But where does this arrow come from if the fundamental laws of physics are time reversible? The answer lies in entropy, a concept from thermodynamics. Entropy is a measure of disorder or randomness in a system. The second law of thermodynamics states that in an isolated system, entropy tends to increase over time. This law introduces an asymmetry. While time-reversible equations describe individual particles, the behavior of large systems follows a different rule. Entropy always increases, never decreases. In the glass shattering example, the reason we don't see the glass reassemble itself is that doing so would require a decrease in entropy, which is extremely unlikely. The increase in entropy provides a clear distinction between the past, low entropy, and the future, high entropy, giving rise to the arrow of time. Let's break down the time reversal paradox in simple terms using relatable analogies and examples. First, reversible equations versus irreversible reality. Imagine a simple system, a ball rolling down a hill. According to Newton's laws, if you know the ball's position and velocity at a given moment, you can predict its motion both forward and backward in time. Mathematically, nothing prevents the ball from rolling back up the hill if you reverse the time direction. However, in real life, we never see balls spontaneously rolling uphill without an external force. Why? Because rolling down increases the ball's entropy. It loses energy as heat through friction with the ground. Reversing this process would require a decrease in entropy, which is statistically improbable. This discrepancy between reversible equations and irreversible reality is the essence of the time reversal paradox. While the microscopic equations governing particles are time reversible, macroscopic phenomena, like a ball rolling down a hill or a glass shattering, are governed by the second law of thermodynamics, which introduces irreversibility. 2. A universe with low initial entropy. Another way to understand the time reversal paradox is to consider the initial conditions of the universe. The arrow of time exists because the universe started in a state of extremely low entropy, a hot, dense, and highly ordered state known as the Big Bang. Over time, the universe has expanded and become more disordered, increasing its entropy. This increase gives rise to the forward flow of time we experience. If the universe had started in a high entropy state, there would be no arrow of time and events might appear more symmetric. The paradox then arises because while the laws of physics are time symmetric, the initial conditions of the universe are not. The low entropy beginning creates an asymmetry that defines the direction of time. The time reversal paradox has profound implications for our understanding of time, causality, and the nature of reality. 1. Time, memory, and causality. One of the key aspects of our experience of time is memory. We remember the past, but not the future. This asymmetry in memory is linked to the arrow of time. Our brains, like all physical systems, operate in a way that increases entropy. Storing a memory involves physical changes in the brain, which increase its entropy. Similarly, causality, the idea that causes precede effects, relies on the arrow of time. We think of events as having causes in the past and effects in the future, but if time were truly symmetric, causality would lose its meaning. The time reversal paradox highlights how deeply our understanding of time is tied to the concept of entropy. 2. Could time run backward? In theory, if the entropy of the universe decreased, time could run backward. However, this scenario is incredibly unlikely, as it would require a massive decrease in entropy across the entire universe. Some speculative theories in cosmology suggest that time might run backward in certain regions of the universe or in a hypothetical multiverse, but these ideas remain purely theoretical. One intriguing possibility is that at the end of the universe, when entropy reaches its maximum, a state known as heat death, time might lose its directionality altogether. In such a state, there would be no distinction between past and future, as all processes would have reached thermodynamic equilibrium. 3. Time in quantum mechanics. In quantum mechanics, time behaves differently than in classical physics. While the equations governing quantum systems are also time reversible, the process of wave function collapse introduces an apparent asymmetry. When a quantum system is measured, it collapses into a definite state, and this collapse seems to occur in a particular direction of time. Some interpretations of quantum mechanics, such as the many worlds interpretation, suggest that time symmetry might be preserved at a deeper level, with all possible outcomes of a quantum event occurring in parallel universes. However, our subjective experience of time remains tied to the increase of entropy in our universe. The time reversal paradox challenges us to reconcile the time-symmetric nature of fundamental physical laws with the irreversible flow of time we experience in everyday life. It shows us that, while the equations of physics might allow time to run backward, the increase of entropy ensures that time, for us, always moves forward. As you reflect on this paradox, consider this. If time could run backward, would we even notice? Perhaps our perception of time is inseparable from the increase of entropy, and a universe without an arrow of time would be unrecognizable to us. The time reversal paradox invites us to ponder the true nature of time, causality, and existence, and reminds us that even the most familiar aspects of reality can be filled with mystery and wonder.